engine and motor. Then this system combines these with the power split device to achieve high energy efficiency. This is the Toyota hybrid system. Each unit has been developed specially for the hybrid system. For the engine, the maximum thermal efficiency has been raised and both low fuel consumption and low emissions achieved. The motor is compact and high efficiency to achieve smooth acceleration. The generator uses the engine rotation to generate electricity, which is sent to the motor and the drive batteries. It is also used as the engine starter and provides smooth engine starting. The power split device contained in the transaxle is Toyota Hybrid Core technology that divides the energy output from the engine between electrical generation and driving according to the driving conditions. The power control unit is the core of the hybrid system. It controls the electricity to provide appropriate amount to each unit. The drive batteries store the generated electricity and supply it to the motor to drive the vehicle. There is no need to recharge from an outside power source or to replace the batteries periodically. They also provide superior durability and heat resistance. Toyota hybrid units have the reliability made possible by years and years of design development and continuous progress. For a Toyota hybrid vehicle, when not moving, all units stop and there is no wasted energy consumption. When the vehicle starts off, the motor drives it quietly and smoothly. For driving at low speed, the motor is used to achieve low fuel consumption. During acceleration, motor drive is combined with engine drive in a rotation range with good engine efficiency to drive the vehicle powerfully, yet with low fuel consumption. The engine drives the vehicle and charges the batteries at the same time to raise the energy efficiency. During deceleration, the rotation of the tires drives the motor to generate electricity to store the power into the batteries for reuse. In this way, a Toyota hybrid vehicle runs the engine in a rotation range in which the engine has good efficiency and that matches the driving conditions and reuses energy that has been wasted until now, and achieves low fuel consumption driving. The Toyota hybrid system is advanced technology that achieves both driving fun and superior environmental performance.
This is the e-motor. The very important aspect. First, a very important aspect before going into electric vehicle segment, you have to understand this. IC engine versus e-motor. Right? So, if I want to tell which is best, obviously my answer is nothing is best. Both are having some plus and minus, positive and negative are there. But someone should be very closer to the requirement, right? In that way, someone is closer. We will understand that. First thing is vehicle driving conditions. So basically an IC engine or a e-motor, both are called as power plant, right? So before selecting a power plant, it is very important that we have to understand what is the driving conditions of the vehicle. So when you look at the driving conditions of the vehicle, the driving conditions are visible here. One is, the first driving condition is moving off. It is the acceleration. So what we mean by moving off means it is accelerating from the rest position, right? So that is a very important characteristic of a vehicle. When we are selecting a power plant, that is a very important characteristic that we have to consider. And second thing is low speed creeping, mostly from cities only, right? Cities only the traffic is there. So we press the accelerator, brake pedal, accelerator, brake pedal, accelerator, brake pedal. This is how we live in cities actually. So this is what we call it as low speed creeping. So we are not allowing the motor to reach or the power plant to reach a certain RPM. Before that we apply brake. So like this we continuously keep on creeping on the road. That is also one behavior. Second, the third thing is acceleration during overtaking. I hope people would have done it, right, in your lifetime many times when you are overtaking in a highway or in a road, especially in the single roads. When you are overtaking, you are seeing that suddenly it's a big truck coming in front of you. Suddenly, what will come in your mind? I have to cross that vehicle and overtake the vehicle and settle down on the left side, right? That's what will come. So immediately, what you will do? You will shift down the gear. You will shift down the gear. I mean, immediately accelerate and you overtake the vehicle, right? So this is an acceleration during overtaking. We call it as sudden accelerations actually, right? Sudden overload also we can call it as. And high speed cruising. High speed cruising, everyone know, it is basically a constant high speed running, especially in the highway. And the the final thing is final behavior of a vehicle is climbing uphill. So that is the gradability. So when I am having an uphill drive, so I have some 10-degree gradient or 20-degree gradient. So my vehicle should be able to climb that gradient, and that is very, very important, right? So these 5 behaviors are very, very important before selecting a power plant for an vehicle. Either it is an electric vehicle or whatever be the vehicle. It is common for all. I hope everyone understand. So the acceleration, low speed creeping, overtaking, cruising speed, and the gradability. So these 5 factors decide which power plant is suitable for which application, right? I hope people are getting the point. Let's first understand a conventional vehicle powertrain, and we will discuss further to understand how it is problematic. Let us look at this picture. So this is an example of a conventional vehicle drivetrain layout. So basically, drivetrain means the gearbox, propeller shaft, differential, and this shaft and the wheel. These components are called drivetrain. When I add the engine or when I add the motor onto that, it becomes a powertrain. First, kindly I request all the students to understand this very, very basic terminology. So what is a drivetrain? Drivetrain means it is the components which is going to support the propulsion of your power plant. And when I add the power plant into the system, it becomes a powertrain. So this is called as a powertrain, including the engine. Whereas the highlighted components are only called as drivetrain. So what are all the components? Can you people identify that? So when I look into an electric vehicle, so this is an example of an electric vehicle layout. So at the moment I come from the previous slide to this new slide, I can readily say that what I can feel from this picture. This is an example of an electric vehicle drivetrain layout. Looking at the previous picture and this picture, what is the difference that we feel actually? So as you see that, what we understand is this lengthier, bigger drivetrain components are missing. That is what mainly for me, it is visible, right? I'm not seeing a very lengthier drivetrain component. Instead of that, what happened is all the drivetrain components have been compressed into a small box like this, which is called as E-axle. So inside this box, we have the power plant. Inside this box, I have the gearbox. Inside this box, I have the shafts. Inside this box, I have the differential. So everything related to the drivetrain component has been compressed into the E-axle. That is a very important change that I can see from this particular picture. I hope everyone can understand that. So the whole drivetrain is being compressed into such a very small space, and that makes what it makes actually. So when you compare to these components are occupying more volume of space, whereas the electric vehicles, the drivetrain components are occupying less volume in space. So what it means is power density. So now the term comes power density. So my power density is very, very higher in the electric vehicle application, or the torque. Basically, power and torque density is very, very higher in terms of electric vehicle. Let's understand it a bit deeper very clearly. So this is an example of a torque characteristic of an IC engine. So students, I request all the people to keenly listen to this point, because this is something which many startup companies or many companies will ask you this question in the interview. This is very, very important. Without knowing this, if you know anything in electric vehicle, that is useless. So when you talk about IC engine, let's understand the torque speed characteristic of an IC engine. if you remember, I have told you 5 vehicle behavior, right? Keep that 5 vehicle behaviors in your mind, and by understanding that, when you correlate this vehicle behavior with this graph, you can see this is the torque versus speed graph of an IC engine. I am seeing 4 problems with this graph. 4 problems with IC engine. One is, you can see the blue color curve. The blue color curve is the torque curve, and the green color curve is the power curve. And what we see, what we understand from here is the torque. First, you see, look at the torque. Look at the torque curve. When a vehicle needs peak torque, when do you think a vehicle needs its peak torque from the power plant, basically? So when the vehicle accelerates, from a rest position, the vehicle has to, the power plant has to give the maximum torque, right? So the moment you start the motor, for example, in this case, this is an engine. In the engine, what happens is, the moment you start an engine, the engine takes nearly 2000 to 3000 RPM to reach its peak torque. So to achieve the peak torque in an IC engine, I have to run the IC engine to somewhere close to 2000, 3000 RPM. And the second problem is, okay, it's not just acceleration, guys. So how quick we want to accelerate, that is much important, right? It is not, I am accelerating from rest position. It is not, that is not much important. It is very important that how quick I am able to accelerate. Say 0 to 60 in 10 seconds, 0 to 100 in 5 seconds, we are telling it. So the time is very, very important. So in that perspective, what happens is, that for that case, constant torque is very important. So when you look at the IC engine, first problem is IC engine achieves the peak torque only after certain RPM, like 2000, 3000 RPM. And the second problem is, it is not maintaining the torque constant. It is immediately fluctuating. It is keep on fluctuating. And the third problem, third requirement for a vehicle is, actually, once you accelerate, what is the next target you want to achieve? We need to go for maximum speed, right? Especially youngsters, you would have seen in signals, youngsters like you, like me, even I am an youngster, right? So youngsters like us, what we do, we look at the signal, immediately the moment the green signal is there, immediately we press the, so once you see that, the youngsters, your signal, before the signal crosses the green, immediately you accelerate, because you want to be the first person in the next signal. Correct. So for achieving the top speed very quickly, you need to have a peak power. So the power plant which you are using in this vehicle should be able to achieve the peak power as early as possible. So the third problem with IC engine is, the power, to achieve the maximum power, the engine has to run 6000 RPM or more than 6000 RPM. Can you imagine? And the fourth problem with this curve is, what is the fourth problem? The power is also not constant. It is fluctuating. So it will come down after a period of time. So 4 problems with IC engines. The first problem is, IC engines develop the peak torque only after running at certain RPM. Second thing is, they are not able to provide a constant torque. The third problem with IC engine is, we are not able to achieve the peak power very quickly. It takes so much of RPM. And the fourth problem is, the power achieved by the IC engine is also not constant. So it's the 4 problems with the IC engine. Okay, is that the only problem? What about the efficiency? What about the fuel consumption rate? When you look at the efficiency of the IC engine, we currently, even after 100 plus years of research, till now people have achieved somewhere close to 40% of efficiency. That's after this 100 plus years, right? And many people have a wrong understanding that electric vehicles are a new technology. It's not like that. Electric vehicles were there in 1830s itself, right? So I hope people know that. So 1830s itself, we had electric vehicles running in the market, and at that time IC engines were the cost of the fuel were very lesser. That is why, and because of the IC engine, all these things, this propulsion system itself changed from electric vehicle to IC engines. And at that time, the power electronics technology, battery technology, all these things were not there. And after 1990s only, we once again started working on the power electronics technology and improvement and all these things. Okay, and that's where we are. So don't think electric vehicle is the old tech. It's a new technology. It's a old technology which was there in the past. It is also there in the present, and even in the future. Even if you call hydrogen vehicle, even if you call fuel cell vehicle, the propulsion is actually going to be electric only. So future, it is also going to be extended form of electric vehicle. So when you look at this IC engine, the problem with IC engine is the fuel consumption area. So actually we call it as, when you look at the engine torque speed curve, we call the engines, wherever the engine is having good efficiency, we call that zone as sweet spot. So we have to have more and more wider sweet spot, correct? That means wider area where more efficiency is there. If I have a very small sweet spot, then I cannot achieve more efficiency. So here is where for example, in this case, this engine is having the sweet spot here, where the fuel consumption is 260 gram per kilowatt hour. Whereas 280, it becomes 280, 300, 324, it increases in all the other regions. So this region is the place where your motor is having very lesser fuel consumption. So it is called as the sweet spot of this vehicle, of this engine, basically, right? So when you look at IC engine today, IC engines, after so much of research till now, they are able to achieve 40% efficiency only. So when you look at the motor, look at the characteristic of a motor. So guys, students, this is very, very important for you. Definitely, if you go for an interview for any electric vehicle company, definitely they will ask you to draw this picture, this characteristic graph. It's very, very important. So understand this. So the motor torque versus torque, the speed characteristic of an E motor. So when you take an E motor's case, now you compare this graph with the IC engine. The first difference that I can see from the IC engine graph and the electric motor is the moment you start the motor starts with the peak torque. The motor starts with the peak torque. And what else the hero is doing? What else the second advantage is giving? He is not only starting with the peak torque, he continues the peak torque until certain base speed. Sometimes it extends till 3000 RPM also. 3000, 4000 RPM also. Today, the modern motors, this is a typical motor. I will show you some real life motors also. So today, the modern motors have a very wide constant speed region. That means the constant torque is extended for more higher RPM. So till 3000 RPM is going to support you. Where it is going to support you. So as I have a very wide constant torque region, my vehicle will be able to accelerate as quicker as possible. So that is a very important characteristic that motor gives for everyone. So first thing is, my motor gives the peak torque from the moment it starts. Second advantage is it continuously gives the peak torque for till the base speed. And the third advantage is the moment my torque starts coming down, my power becomes constant. My power becomes stable, right? That is the third plus point. And you know how much quick the power will become peak. That is very important. In a typical motor, around 2000, 3000 RPM itself, your motors can achieve the peak power zone. That is one more plus point that motors can give. If you remember IC engines has to run somewhere close to 6000 RPM or 5000 RPM to achieve the peak power. So I have to burn that much fuel. So can you understand that how much good the motors are in terms of traction purpose? And the fourth plus point the motor gives is the motors are able to maintain a constant power region. You cannot say it is 100% constant. It's not flat curve, but still it is called as a CPSR. We call it as constant power speed region. So motors exhibit a wide constant power region. So looking at the constant power region, we can understand that when you have a wide constant power region, you will be able to play with the motor in its most efficient region. Say in the previous picture, I have told you that IC engines have a very small sweet spot. Sweet spot means this is the region. This is the region where IC engine is very efficient. That means, for example, when I will take a point from this sweet spot, say 120 Newton meter at 3000 RPM. For example, this point is a example of a sweet spot. So when you look at IC engine, the sweet spot is smaller. And when you look at the motor, look at our motor. Our motors have a wide sweet spot, wide region where highest efficiency is possible. That is one more plus point. And second thing is the minimum efficiency. When you look at the IC engines today, after 100 plus years, the maximum efficiency that the IC engine has achieved is whereas close to 40% right now. That too only few companies, not all the companies, right? But when you look at the electric motor, if you remember when you studied the electric motor, the books itself tell you 85%. Am I right or not? In our books itself, we can see that motors are giving 85%. Yes, So what do you think real time? Because you know our books and real time will not match in India, right? I hope everyone can accept this, right? Nothing will in India. If you say the curriculum, it will not match exactly with the real time requirement of the industry. Right now, the industry actually has motors in the electric vehicle segment with capability of achieving 96 to 98% efficiency, right? Even though if your books are telling 85%, that may be a generic value, but today there are companies which are running their motors at 96 to 98% also. So electric motors have the ability to run at very, very higher efficiency, because very simple thing is we don't have so much moving components. That's a very simple thing. This is what we call it as cradle to grave study. Cradle to grave. That means when you see a vehicle, for example, a passenger car, how much amount of carbon dioxide emission. So first understand the cradle to grave. That means when I am producing my vehicle, so when say for example, when I'm manufacturing my vehicle, how much is the amount of CO2 I'm generating during my raw material extraction, during my component manufacturing, like manufacturing of door, manufacturing of frame, manufacturing of suspension, all manufacturing, and then vehicle manufacturing, right? And this is called cradle to gate. And then after manufacturing is done, I'll be running the vehicle on the road. So while manufacturing, I'll be generating some CO2 emission. While running on the road, I'll be generating the CO2 emission. This is called use phase. So this is called production phase. So this is what we call, and after the use phase is done, we need to recycle it. So for recycling, how much carbon dioxide emission is done for all these vehicles? So here we are going to compare conventional petrol engine, diesel engine vehicle with an electric vehicle. Let's see who is polluting more in this industry. This is an example study done by Volkswagen. You can see that Volkswagen has done this cradle to grave study, and they came to know that, you know, Volkswagen has a model called Golf, Volkswagen Golf. The Golf, they are comparing the Volkswagen Golf diesel vehicle with electric model of their Volkswagen Golf, and you can see that the diesel model, on the whole lifetime, on the whole production, use phase, recycling, everything included, on the whole lifetime, it generates 140 gram CO2 per kilometer, whereas an electric vehicle, the electric model of the same vehicle, generates 119 gram CO2 per kilometer. So this is one first thing that you have to understand. So what we understand is electric vehicles are not completely clean. I'm not here to say you that electric vehicles are very, very, very clean. That's not true, right? Electric vehicles are not clean enough, but still they are clean enough compared to IC engine. They are not polluting like IC engine. When you look at the IC engine, the most of the pollution that happens is in the supply chain of the fossil fuel and in the combustion. That means to develop the petrol and diesel from the oil, from there lot of CO2 is being ejected, and then when the petrol comes into your vehicle, in your engine, there you are burning every day, you are burning the petrol and diesel, there the CO2 comes. So these are the two areas where the CO2 emission is more in a conventional vehicle. So what you understand from here, the diesel engine reaches 111 gram per CO2 per kilometer, right, during this phase. And whereas when you take the electric drive only during the generation of electricity, right? We use the coal, we use some different form of electricity generation. So that is the area where the emission is being produced. That is not the only area, guys. Even in the production phase, electric vehicles pollute nearly 57 gram per CO2 level of CO2 during the production phase only. Because you know, electric vehicles have many unique raw materials like lithium, like many nickel, cobalt, so many unique raw materials, and these raw material, even rare earth magnets used in the motor, and lightweighting materials for the EVs, all these are special materials which requires additional support, additional effort. So electric vehicles compared to petrol and diesel vehicle, during the production phase, electric vehicles generate lot of CO2, but in the usage phase, electric vehicles have lesser CO2 compared to the petrol diesel vehicle. So overall, if you see that electric and diesel vehicle, electric vehicles overall, it develops lesser CO2 per kilometer only. And you can understand from this graph also that this is the blue color one is the battery production. So that is where most of the emission is happening, and the car vehicle production, that is where other remaining part, and the driving part. That means when you charge your electric vehicle, your electricity. So the electricity, where it comes from, that is a big question now. So electricity generation, India is currently generating nearly 64% of its electricity from thermal sources, coal, lignite, and only 21% of India's electricity is coming from renewable sources. It's huge potential. You can see India's just 35 gigawatt of solar power capacity till now. So when you increase the solar power capacity in India, then our usage space will become greener. So our electricity will become greener. Then I can say that these emissions will come down. This 119 gram CO2 per kilometer will come down definitely when we use the renewable energy sources. Not the only push enough for bringing electric vehicles in India. That there is one more push called CAFE norms. There is one more push called CAFE norms. CAFE. That is called as Corporate Average Fuel Economy. So the global level, there's a push on the manufacturers, on the vehicle manufacturers, that they have to reduce the gram per kilometer value of their vehicles. See, the Department of Energy of United States of America has set a target for many manufacturers in the world. Has a set of target for the electric propulsion system. What is the target? For example, the electric motors. Today we are using so many motors. We are using electric motors like induction, BLDC, PMSM, reluctance motor, many different motors. But without any target, if you work, you will not be able to achieve. So this DOE, Department of Energy, is a very high-level organization in America. So this organization set some targets for the technological development. So this company has set a target of achieving by 2015. They set a target of $7 per kilowatt of motor, and they set a target of power density of 5, for example, 5 kilowatt per liter. That was the target they had. The volume. So how much kilowatt your motor is able to generate per unit volume. Correct? That is what they call it as the power density, and you can see that it is, they have a target. So Department of Energy has set a target of 50 kilowatt per liter. 50 kilowatt per liter. That means what it means is the motors has to become smaller and smaller and smaller and smaller. That is what they mean. The motors can no longer be bigger. They have to generate more power. At the same time, the motors has to be so much smaller. And you can see that by 2025, the target set was nearly 50 kilowatt per liter. And for power electronics also there is a target. That is a very big target. It's not a small target, guys. Power electronics means what? It is our inverter. It is our inverter component and DC-DC converter component inside your electric vehicles. And the Department of Energy has set a target of achieving 100 kilowatt per liter as a target. Right now, by 2015, actually in 2015, we were at 12 kilowatt per liter of power density on the power electronic side. That means basically this determines the power density of your IGBTs, switching devices, semiconductor devices. So the Department of Energy has set such a very positive, ambitious target. So because of this target, what will happen? All the companies who are working in semiconductor devices, IGBTs, MOSFET, they will try to make their devices smaller and smaller and smaller. Not only smaller, they will make the when you make smaller, what will happen? Their ability to withstand temperature will reduce. So they also should make sure that the temperature problems will not come. So they are trying to size the whole power plant in a very smaller size, right? So that's what I hope people can understand, that is the target that they are setting. So not only the power density target, they are also setting target for achieving the low cost. So current by 2025, they are targeting $2.7 per kilowatt. That means, for example, if I have a motor of a two-wheeler might need a motor of 3 kilowatt. For example, I'm telling. So 3 kilowatt. Can you imagine? It is 2015. It was $1 per kilowatt. but so for 3 kilowatt. So you can imagine that how you can project it by 2025, how it will be. So you have more and more documents. You visit the Department of Energy website. You will come to know that it is not just from for 2025. Even they have set targets for 2050 up to 2050 also. So all the manufacturers are currently working on this particular target only. So drivetrain level, this is on motor level, this is on power electronics level, and this is on complete drivetrain the electric traction drive system level. So this is the target given for these companies. I hope you people can understand the point, right? So that's the first point of understanding, guys. That's the level 1 of understanding a basic electrical architecture, right? I hope I'll just go back to the few slides. Basically, we have the epicyclic part. I told you very clearly that epicyclic gears are the one which is working in the hybrid vehicle, which makes it more efficient and more effective. This is the picture of the whole global thing. You can see India is at this point. So Indian government has set a target of 113 gram per kilometer. That means only vehicle which meets this target, they can sell their vehicle in India. So if you look at Canada, it is 99 gram per kilometer. They have set a target because Canada is a country which actually works on more cleaner air. So they are 99 gram per kilometer. China is coming down, and China is planning to reach 117 gram per kilometer by 2020. So India is right now not right now India is actually having 130 plus gram per kilometer, and right now we are targeting 113 by 2020. So all the manufacturers of the world are being pushed or being pressurized to meet this target of gram per kilometer. So now the question is how they are going to meet it, right? Whether I'm going to use the same petrol and diesel engine, I'm going to meet it, or I'm going to use a hybrid vehicle, or I'm going to use a electric vehicle, or a hydrogen, or fuel cell, whatever be the type of vehicle. End of the day, the target is this gram per kilometer only. Okay, so if the company is able to meet the gram per kilometer target with IC engine itself, then they will go with IC engine only. But as per the current study, most of the companies are unable to achieve these targets with IC engine only. It is not possible. 100% it is not possible. So people are moving for other aspects and the other methods of propulsion. We will try to understand that in the coming slides. So this CAFE norms, corporate average fuel economy norms, that is the one which pushes the companies to go for some other propulsion. Instead of using petrol and diesel engine, they are moving for other propulsion. So instead of directly moving for electric propulsion, one of the way that they can achieve these CAFE norms is the hybrid architecture. So now this is one of the way with which they can achieve the CAFE norms. So hybrid architecture is one of the area where currently markets are growing right now. Compared to electric vehicle, hybrid vehicles are having many good advantages. Let us discuss about that. So when you look at the hybrid powertrains, basically, so in India, you might have seen some companies like Maruti and Mahindra. They would have sold something called as micro hybrid and mild hybrid. Have anyone heard it? Those micro hybrid and mild hybrids are basically like small motors, and especially micro hybrid is only for start and stop during starting time, and when your vehicle is on the signal or anything, then only it will work. And you have a mild hybrid where it will have a small electric motor and a bigger engine. So in this case, the motor will be able to support your engine, but it will not be able to run your vehicle completely with motor itself. That is called mild hybrid. Next part of other than the micro hybrid and mild hybrid, we also have the full hybrids. So in that case, the motors will be quite bigger. The batteries will be quite bigger enough to run the vehicle in pure electric vehicle mode as well. So you have the hybrid vehicles like Toyota Prius. So these vehicles are coming under the full hybrid vehicles and plug-in hybrid vehicle. So plug-in hybrid vehicles means you can charge these vehicles from the external socket, but normal full hybrid vehicle means the charging will take place only with the engine present inside the vehicle. So the engine inside the vehicle only will charge the battery inside it, and you cannot externally charge it. So if you call it as plug-in hybrid, then you can externally charge the vehicle. That is called plug-in hybrid. So Toyota Prius has both the plug-in and full hybrid vehicles. And the other one is the full battery electric vehicle, and the other one is the fuel cell electric vehicle. Hybrid scenario here, we have the P1 hybrid, P2 hybrid, power split hybrid. So what is meant by these different hybrids? It is nothing but where you are going to position the power plant, your motor, where you are going to position the clutch between the motor and the transmission. Depending upon the position of the clutch between the motor and the transmission, you will have different classifications. P1, P2 hybrid. Say P1 hybrid, the example is Honda Civic, and the P2 hybrid, Infiniti, that's an example. And power split hybrid, best example would be Toyota Prius, right? Let's understand what is meant by these different hybrids one by one. The first one is the series hybrid. What is meant by series hybrid? The very important thing that we have to understand in series hybrid is, in this case, so hybrid generally, what is meant by hybrid? Hybrid means two power plant. So in the series hybrid, you can understand that the IC engines, the sole purpose of IC engine is just to generate electricity for the battery, and your IC engine will not directly propel your vehicle. That is very important. You have to understand. In series hybrid vehicle, your engine only acts as a generator, and it will charge the battery, and the battery provides the electric power to run the motor, and the motor is the only power plant which is going to propel your vehicle directly. That is a series hybrid. And this is the case of parallel hybrid. So a parallel hybrid is the case where both IC engine and electric motor join together and propel the vehicle, depending upon what is the driving condition, whether my vehicle is starting, whether my vehicle is accelerating, whether my vehicle is in gradient, whether my vehicle is overtaking. At different point of time, your different power plant may join together or may work independently also. Means what? Depending upon whether the total torque requirement of my controller will decide whether I have to take the power from both IC engine and motor, or my power from the motor itself is enough to propel. So depending upon the controller signal, it will be determined whether, but the thing is, understand that parallel hybrid, both can help to directly propel your vehicle because both are connected to a clutch mechanism. So as I mentioned both the power plant, both the engine and the gearbox join together and propel the vehicle. And this is the third part. We call it as series and parallel hybrid. We call it as like power split hybrid. Let me show an example. So this case. So this is an example of a power split hybrid. Now let's understand very clearly what is this power split hybrid. Look, this is what the unique thing, this is what the gearbox used in the power split hybrid. So in mechanical engineers, you might have known that there is a gear called epicyclic gear. Epicyclic gear. We generally use this gear in the automatic transmissions. Epicyclic gear. So epicyclic gear will have a sun gear, we'll have a planet gear, we will have a planet carrier, and we will have a ring gear actually. So in Toyota Prius is an example of a power split hybrid. So Toyota Prius, basically what is happening in Toyota Prius, we are using 3 power plant, 1 IC engine and 2 motors. The IC engine is connected to the carrier gear, and the motor, one of the motor is connected to the sun gear. And what happens here, when you run your engine, when you run your vehicle, depending upon what is the driving condition, whether you are accelerating, depending upon the demand from the controller, that the controller will decide whether I have to actuate the engine or not. So what I will do, this is the one-way clutch. OWC means one-way clutch. So using a one-way clutch, what I can do, I can connect my sun gear with the planetary gear carrier and the ring gear. I will show the pictorial representation in the coming slide. So what will happen, when I need a more acceleration, my engine output will combine with the sun gear output from the motor 1. This is called motor generator 1, and the output will go to the ring gear, and the ring gear is actually connected to a gear pair where your motor 2 is connected. This is quite complex, right? You can understand that Toyota is using actually 2 motors, 1 IC engine. So they want to see why Toyota is using this much components, because of the different driving requirements, different driving conditions and requirements. Toyota wants to efficiently use these motors. What happens is, say whenever my charge is completely down, whenever there is no charge in my vehicle battery, then immediately one of the motor will be acting as a generator and the other motor will be working as a motor propulsion. So what happens is, all these both are actually motor generator units. So what is meant by motor generator unit? Because we call it as motor generator unit because they have the capability to work as a motor as well as the generator. So what happens is, end of the day, what happens is, what is the efficiency that Toyota Prius has achieved? What is the mileage of the car? Can anyone tell me what is the mileage of this car? How much kilometer per liter do you think? Toyota Prius. So the answer is actually 40 plus. Currently, this car is having a mileage of 40 plus kilometer per liter. So we understand that yes, they use motor, they use two motors, one ICE engine. But what we understand is they use all these components in their most efficient region. If you guys remember, do you guys remember I have shown you some sweet spot graph. Sweet spot graph. If you remember the ICE engine graph of the efficiency plot and the motor efficiency plot, I have shown you some sweet spot. So what Toyota is doing is, Toyota is actually running the engine in its sweet spot only and running the motor only in its sweet spot. That means where the highest efficiency is. So because of this combined highest efficiency of motor and engine, the whole vehicle has been able to achieve that magic number of 40 km per liter. And right now Toyota is targeting 48 km per liter by 2022, right? So they are already working on it. So what we understand is basically Toyota Prius uses two powertrains. So they use the PMSM motor. So other than Toyota, even Chevrolet is also one of the manufacturer which has went to this hybrid system. But Chevrolet is quite different. What they have done is Chevrolet is having some different operational modes. You can see that they call it as charging depletion mode and one more mode called as charge sustaining mode. One is called as charge depletion mode and one is called as charge sustaining mode. So depending upon how much total battery, so capacity available in the battery, the controller will decide to which mode it can work. Either both the motor, say for example in this case you can see one motor EV mode. One motor EV mode. So in this case, when this mode is there, when this mode is taken, you can see that when the low and medium torque demand is there, any speed, including reverse or combined speed, say you can see that low and medium torque speed, you can go for this mode. And whenever high torque demand is required, then the mode shifts to two motor electric vehicle mode. So depending upon the requirement, yes, at the end of the day, it is the torque requirement or propulsion requirement. And you can see this picture. When this low extended range is required, low extended range mode is required. When you have a high torque demand of from 0 to 60 km per hour, and basically, so what happens is in this case, your IC engine runs this motor and charges the battery. Can you see that? So your IC engine keeps on charging your battery. At the same time, propulsion is also taking place. So depending upon how much charge is available in the battery, the modes will change from battery to different, either a depletion mode or the vehicle will work in the charge sustaining mode. So if you have a very high state of, if the battery is very highly completely charged, very high state of charge, then they will work on the charge depletion mode. And if the charge is very low, then they will try to maintain the sustaining mode. They will try to maintain the charge in a stable way. So we call it as high extended range mode, low extended range mode, and fixed ratio extended range mode. I don't want to go deeper into that, but understand as a student level, kindly understand that hybrids have the ability to combine the different operational modes of the vehicle, say different operational modes of the components. So the engine can operate at a different point of time in the vehicle, and the motor 1, motor 2 can operate at different point of time in the vehicle. Components in an electric vehicle. So today people think just motor and controller makes the electric vehicle. Let's understand what else the components are there. So when you take an electric vehicle, when you look at the components in an electric vehicle, look at the thing. The number 1 component is the electric motor. The number 2, high voltage battery. Number 3 is you have the high voltage distributor. And number 4, you have the power electronics. That means your inverter to run your motor. And number 5 is the compressor, air compressor. We'll talk about that. And number 8, where is number 8? So here's the PTC heater. And number 9 is the DC-DC converter. Number 6 and 7 is the charging system units, fast charging and onboard charging units. Let's understand one by one. So basically all these components come under the high voltage component. Any vehicle, any component which is crossing, which is equal to or more than, look at the answer very clearly. Any voltage, DC, for DC, if it is equal to or more than 60 voltage, it is called high voltage. And if it is AC, If it is equal to or more than 30 volt, it is called as high voltage. I hope the answer was clear. Once again, I am repeating. If it is a DC, it is equal to or more than 60 volt. Anything which is equal to or more than 60 volt, it is called as high voltage. And anything which is equal to or more than 30 volt, it is called as high voltage in AC. So many people think that high voltage means something close to 11 kV, 11,000 volt, 12,000 volt, 20,000 volt, like that. But in automotive perspective, the things are different. Okay. So when you look at the electric vehicle, all these components which are looking, these components, most of the time, they are coming under the high voltage category. The electric motor, the propulsion, the power electronics component, the inverter which is going to run your electric motor, and your high voltage battery, and your high voltage distributor. The distributor is basically nothing but a junction box. You know junction box. We use a junction box in our home. So this junction box is like that. What it does, it connects the high voltage battery to different other components. Say it connects the high voltage battery to the DC converter. It connects the high voltage battery to the heater. It connects the high voltage battery to the compressor. So basically it is a junction box where it connects the main high voltage battery into other high voltage components. That is called as high voltage distributor block, right? And you also have a unit called fast charging unit and the onboard charger. Fast charging unit is basically a unit which takes the DC power directly and gives it to the battery. And onboard charger unit is nothing but AC to DC converter. It is the AC to DC converter which converts your AC power from the charger and converts that into DC and then charges your battery. And this is what the AC charging and DC charging. And the ninth component is the DC-DC converter. So when and where the DC-DC converter is used, see the DC-DC converter, what I mean is actually that is quite different. Okay. So in this case, say as you told, every inverter, every controller component will have a DC-DC converter inbuilt, because for supplying low voltage supply like 5 volt, 4 volt, like 12 volt inside the controller component, you need that. But what the high voltage DC-DC converter I mean, that is different. The DC-DC converter, what I mean is completely different. Say in your electric vehicle, either electric vehicle or conventional vehicle, you have the headlamp, tail lamp, you have the horn, you have the windshield wiper, these kind of accessory components. And these accessory components need to have somewhere close to 24 volt, 12 volt supply. Whereas the high voltage which is provided your battery of your electric vehicle will be in the range of 300 plus 200 plus voltage DC. So these voltages cannot be directly used by your accessory of the vehicle like headlamp, tail lamp to operate your accessories. So we need to have a DC-DC converter which converts your high voltage like 300, 400 voltage into 12 volt, 24 volt output, and then that is supplied to the accessory battery through the charging the battery. I hope you people are getting the point. This is the E-axle we are talking about. So the E-axle, what we mean is the motor and the transmission part and your differential. This is what the E powertrain, and you also have the inverter very close together, right? I hope you people are able to see this picture. This is the motor, and this is your transmission gear, and this is your differential gear, and this is your parking gear. Basically, the transmissions will have a parking gear, and this is how the electric propulsion will look like. We'll discuss in detail. And the next important component that comes to so to run this propulsion unit, what you need? You need an inverter. So this propulsion system, basically these motors need an AC input, a 3-phase AC input. So we need a inverter to do this job. So this is an example of an inverter, and this example I have taken from Toyota Prius. In Toyota Prius, you know how many motors are there? Because of that 2 motors, you are using the 2 switching device systems. You can see that one inverter system for one motor and another inverter system for one more motor. So these are the switching devices, the IGBT or switching devices basically to run the motor. And we also have, so addition to the motor, the inverter used for propelling the motor, you also have one more system called boost converter. So can you people guess what is it for? It is used in hybrid vehicle application. See, actually, when you look at hybrid vehicles have lesser size of battery compared to the electric vehicle. Do you agree this? Compared to a pure electric vehicle, hybrid vehicles have the battery packs lesser, smaller in size, smaller in capacity. right? So basically what happens is when you accelerate an electric vehicle, these boost converters are basically kept between the battery and the motor. They are kept between the battery and the motor. So what happens is these boost converters supports the way to boost the voltage or during the acceleration stage of my vehicle. Say for example, my battery pack, what I'll be using in an hybrid vehicle will be in the range of 200-300 voltage only. But to propel the electric vehicle, you may need to have somewhere close to 400 voltage. And because of this high voltage requirement, if I choose a very bigger battery in hybrid vehicle, that will what will happen? That will increase already the hybrid vehicles are higher in price. So I cannot put a bigger battery. So instead of that, what I'm going to do, I'm going to create the presence of a bigger battery for a short period of time. Why we need a bigger battery? Because we need to have a higher voltage, right? So in this case, what we are doing is whenever I am accelerating my vehicle, I need to have a higher voltage, right? Only during that particular point of time only, I need to have a very high voltage. After acceleration, I don't need very high voltage actually to operate the vehicle. So these boost converters, what they do actually, they act only in the certain period of time of the operation of the vehicle. When the vehicle is starting, initially what will happen? The propulsion power is not provided directly by the battery. The propulsion power is provided by the smoothing capacitor. Let me show the pictures in the coming slide. So we use a smoothing capacitor in parallel with your motor inverter. So what happens is when you accelerate, the moment you accelerate the motor, the power comes from the capacitor only. Understand that it is not coming directly from the battery. If the battery is taken directly from the battery during propulsion stage, it will damage the battery. So such a high voltage is not directly feasible from battery packs. So people go for boost converter where, for example, 200 voltage will be converted into high voltage of 400 voltage, and that will be stored in the capacitor. And the capacitor has the capability to supply huge amount of power to the motor during the acceleration time. I hope you people are able to get my point. And similarly, when this capacitor will be useful? During, say, when I'm switched off the car, now I'm turned off the car. After turning off the car, what will happen? So if you take a petrol diesel car today, when you turn off a petrol diesel car, the petrol and diesel which have went to the carburetor or your injection system will be blocked. It will be returned back to the fuel, right? Returned back to the storage reservoir. Similarly, in an electric vehicle, we have the capacitor. This capacitor, when you turn off the car, immediately the power which is flown towards the inverter will flow back to the capacitor, and this capacitor will discharge it through a resistor, right? So basically the boost converter is assisting in that area. So we call it as a reactor. So it's basically an inductor. So this reactor helps you to dissipate the energy when you turn off an electric car, and this reactor acts as a boost converter when you want to accelerate an electric vehicle. So this is the sole purpose of using an electric boost converter in an electric vehicle. So boost converter helps you to reduce the battery size. Instead of putting a 400 volt DC battery, I can run the vehicle with a 200 volt battery itself. Are you people clear? Actual inverter will look like. This is your 3-phase output cable coming from the inverter. Where it is connected? It is connected to the motor. When you open that inverter, you will be able to see these components. So basically what is there inside an inverter of an electric vehicle? So one of the important aspect is the switching devices. So you need to use switching devices to run the electric motor. Understand that we use power electronic switching devices like IGBTs. This is what the IGBT, how it will be looking like, the IGBT module. So you have two IGBT in Toyota Prius. If you open, 2 motors are there. So you have totally 6 IGBTs are required to run one electric motor. So since Toyota Prius is having 2 motors, 6 plus 6, 12 IGBTs will be there. In addition to that, we use a boost converter. You know how a converter will look like. A converter will need to have a switching device to on and off. So you have another IGBT module. So totally 6 plus 6, 12 and 12 plus 2, 14. 14 IGBT modules are there inside a Toyota Prius inverter. And in addition to that, we also have some sensing requirements. So the inverter also has some current sensors. We'll also have some temperature sensors to continuously monitor the temperature of your IGBT, temperature of your inverter components, and accordingly, the cooling system of your electric motor, the inverter system will be operated. So this is the inverter the hybrid vehicle of the Toyota Prius will look like. And when you go to the battery pack, this is an electric vehicle battery pack, how it will look like. So from the battery pack, if you open the battery pack, you will see the modules. And when you open the modules, you will see the cells, an electric vehicle battery cells. So these are all makes an electric battery pack basically. So cell to module to pack, how a battery pack of an electric vehicle will look like. And once you look at battery, you will also come to know the temperature issues. So to solve the temperature issues of an electric vehicle, you need to have a thermal management system. So the thermal management system, what you are seeing in front, this is the example, a typical thermal management system of an electric vehicle. So people think electric vehicles are very simple to make. It is not like that. So when you look at electric vehicle, you have a lot of thermal management issues possible. So you have a traction motor, you have an inverter, you have a DC-DC converter, you have the vehicle control module, we have the onboard charger, and you know one thing, all these components are developing or generating a lot of heat. So the problem is, like an IC engine in your vehicle, electric vehicle also needs to have a proper thermal management system. If that is not done, then your vehicle will not be able to operate properly. So electric vehicles have a lot of thermal management issues. So electric vehicles should have all these components to make sure that thermal management is done properly. Then you can look at one thing, the electric pump, that is the compressor part. Now my question, look at the picture. This is the compressor used in an electric vehicle. Now there is a question for the participants. Can we use the AC compressor, what we use in our petrol diesel vehicle today, in an electric vehicle? Is it possible or not? So the answer is no. We cannot use the conventional air compressor, AC compressor of a petrol diesel engine directly in an electric vehicle. The reason is, if you remember a conventional vehicle, you have heard that when you start your vehicle, you should not start your AC before starting off your conventional vehicle. You would have heard it, right? So what it means in conventional vehicle, IC engine propulsion is required to run the AC compressor. So without IC engine turned on, your AC compressor will not turn on. So this is not the problem. This is not the case in electric vehicle. In electric vehicle, there is no IC engine. So I cannot depend on the IC engine's propulsion. So what I need to have? I need to have a separate motor. I need to have a separate controller. That means I need to have a separate inverter for the motor. I need to have a special AC compressor for the electric motor. This is what the special AC compressor of an electric car will look like. And this is basically used in the thermal management system of an electric vehicle. So whenever your battery temperature goes high or low, you should have a special AC compressor. So understand that IC engine vehicles, the AC compressor is completely different from the electric vehicle. So these compressors are basically having the capability to run at high voltages. They can run at high voltages even without the presence of IC engine. That is the specialty. And you have the integrated inverter. It's a very small component, and you have the inverter and the motor integrated inside this compressor. That is the special nature. And you also have the PTC heater. So when your battery pack or anything, when your electric vehicle goes into extreme climate conditions like minus 50 degrees Celsius or plus 50 degrees Celsius. So when your battery goes to minus 50 degrees Celsius, you will have a PTC heater, right? Positive thermal coefficient heater. And these heaters make sure that the electric vehicle's temperature of the coolant is raised to a certain level, that the components are working in a proper way, right? I hope you people are getting the point. So these are the two important components, a major difference between a conventional vehicle and an electric vehicle. And we also have one more major important component, that is the relays. Look at this picture. So today's session is to understand that there is a heater, that there is a compressor that is different from a conventional vehicle. I hope you people get the point. Today's agenda of the session is to make you people understand these are the components in a vehicle. And the next very important component that we have in an electric vehicle is the relay. It's a very, very, very important component in an electric vehicle. So basically, you have a battery, you have an inverter. I told you, like today, if you take a car today, you have an ignition system. So you switch on the key, you start when you press the accelerator, immediately your petrol will start flowing from your petrol tank inside your injector, and it will go inside your IC engine, correct? Same way, here also, you have something like that, but here it is the relay. Here you call it as a relay or a contactor, basically. So this is it is a switch. So this is a switch between your battery and your inverter. So whenever you turn on your car, it is this switch that connects your battery and your inverter. And you can see the contactor, green color. There are two contactors. I'll show you how it will look like. This is how the contactor will look like. Wait for the picture. So hope the participants are able to see the relay. Yes, relay. This is the contactor that I am talking about, that is used in the electric vehicle. This is how the contactor will look like. What we will do, this contactor will be connected, one end of the contactor will be connected to the battery side and one is connected to the inverter side. Let me come back to the previous slide. So now what I'm going to do here, I'm going to place a contactor in between the battery and the inverter. And this contactor is very important because when you turn on an electric car or turn off an electric car, these are the contactors are going to operate. One more question, contactors here, two green contactors. That means the green contactors are called main relays basically. Why we have two main relays? That's my question to the participants. Why we have two main relays? Look at this picture very clearly. There is a clue in this symbols. You have to see that those batteries, the negative terminal is always connected to the chassis frame of the vehicle. Have you seen that? The body of the vehicle, it is connected to the body of the vehicle. Have you seen that? Negative terminal of the battery. So you have two separate contactors here. So if it is a low voltage during any accident or any kind of problem in a conventional petrol diesel vehicle, it is just 24 and 12 volt. So basically it will not have any impact on your vehicle, basically on the chassis. But if it is an electric vehicle, it is somewhere close to 600 voltage DC, 600,000 voltage DC in an electric bus and electric truck. In that case, what will happen? If there is any leakage to the chassis frame, it has the capability to melt your whole chassis frame, right? So what happens is, both the positive side of the connection on the negative side of the connection, it is very, very important. Even at the same time, even if one contactor fails, if one of the contactor fails, at least the other contactor will stay in contact and it will be operating. So for the safety, we call it as safety check purpose also, we have two contactors. Even if one contactor fails to operate, worst case scenario, these contactors are actually tested to their extreme level. But even you cannot say anything can happen in this world. So these you have a backup contactor. So one is connected to the positive side of the battery and inverter, and one is connected to the negative side of the battery and inverter. Negative terminal is connected directly to the inverter, and the negative terminal is also connected to the inverter only. Here there is no grounding happening on the frame. This is a very, very important thing that people should understand compared to a conventional vehicle. So to perform the redundancy check, always the battery controller will check both the contactors are open or closed. So we also have a pre-charge relay. You can see this pre-charge relay and pre-charge resistor. What is this pre-charge relay? Now can you guess it? Pre-charge relay, and you can see the capacitor. Now do you remember something I told in the beginning of the session? So this pre-charge relay, when you start the electric car, correct? When you start the electric car, when you are accelerating, you will be expecting more huge amount of current. I told you batteries cannot directly supply that huge amount of current. They will be supplied to a smoothing capacitor, especially in passenger cars and trucks and buses. Smoothing capacitor, especially when you switch on the car, immediately this main relays will be opened and this pre-charge relay will be closed. And the battery power from the battery will go to the pre-charge relay and it will go to the capacitor, and your capacitor will be charged 80% of its capacity. And when the driver press the accelerator pedal, immediately the power from the battery, that means power from the capacitor, goes to the inverter instead of the inverter asking from the battery. And once the acceleration has happened, then your main relays will close and your batteries will directly start supplying the power to the inverter. Is it clear? And now same thing happens in the negative side. That means on the turning off side, when you turn off an electric vehicle, what will happen? There will be some power gone to the capacitor and inverter. So what will happen? I have to dissipate that power. So what will happen? When you turn off an electric car, this pre-charge relay will come into picture. It will open. It will close the circuit, and what will happen? This pre-charge relay will, that means the pre-charge resistor will absorb the current, the power available in the capacitor, and it will dissipate it in the form of heat. This will take up to 5 minutes when you turn off an electric car. That is why always remember, not only electric car, guys, any vehicle which is having higher voltages. Okay, so this resistor will dissipate the power which is being taken by the capacitor at the switching off after turning off the electric car. So understand, pre-charge relay play a very important role in turning car, right? So relays play a very important role. Other than that, relays also work in the accessory region where they charge the batteries, high voltage batteries are connected to the DC-DC converter. Is it really safe during a crash? Yes, electric vehicle is safe during on the 4th day, we are going to discuss more on the safety. Don't worry, nothing will be missed by me during the sessions. So you have also relays used in the relay on the switching, on the charging part, as well as the accessory. And you can understand this is the real-time component. So this component I have taken from Chevrolet Bolt. That is an electric from Chevrolet. Very famous. This is what contactor. This is a pre-charge contactor, the relay I was telling, and pre-charge resistor. This is the block where these components are mounted generally. Okay. This is what the actual components will look like. And this is what the actual relay, the contactor, what we are talking about. Now, what is the speciality of this component? What is the speciality of this relay? These components are very. You can look at this picture. These contactors, you know what is the operating time of this contactor? Less than 2 milliseconds. The moment the electric vehicle controller detects the problem in an electric vehicle, within less than 2 milliseconds, this relays will open the circuit. So within 2 milliseconds, the batteries will become special that they are having a dust-proof structure, a waterproof structure, because these are very important, right? Because dust or something enters the contactor and creates problem that is not acceptable. And also, other than the cable, let me write. I hope people are able to see the screen. It is the high voltage cable used in an electric vehicle. Electric vehicles use special cables. Special cables. They are not using the conventional cables used in our appliances. Right? Electric vehicles use special high voltage cable, and orange color is the coding for high voltage. Whenever a system is having, so now can you participant tell me above which voltage it is called high voltage in electric vehicle? Let's see. Yes. So it is equal to or greater than 30 volt AC and equal to or greater than 60 volt DC. So how to identify there is a high voltage by the color coding when the it is orange. And basically when you look at the cut section of a high voltage cable, other than the copper conductor, we will also have an insulation. We will also have a braided sheath. A braided sheath will be there. This is basically to avoid electromagnetic interferences, to prevent the conductors from the electromagnetic interference outside. So basically these cables used in electric vehicles have ability to withstand higher loading, higher EMC shielding will be there. At the same time, even though they are this much thick, they also have the exceptional flexibility, also very important. Let me show you a cross cut section of a high voltage electric vehicle cable. When you look at the electric vehicle high voltage cut section, this is how it will look like. The outer jacket is there. After the outer jacket, you also have a film insulation. And after the film insulation, we have a braided shield and sheath and a primary insulation, and we have a conductor, core conductor. So basically the insulation is provided to prevent the losses from the core conductor, and you also have the braided shield basically to prevent the EMI EMC problems, electromagnetic interference problems. I will explain you this EMI EMC issue detailed in the 4th day session. Okay, so it is basically a electromagnetic compatibility and interference problem. Then these high voltage cables are very special, designed for that, to withstand that. And other than that, we also have some high voltage fuses. So electric vehicles also use some high voltage fuses. So if there is any electric vehicle, the problems in the electric vehicle in terms of safety, any type of malfunction happened, immediately a fuse will be there. This fuse has the capability to withstand up to 20,000 ampere. Can you look at it? 20,000 ampere it can withstand. So it's a very special fuse used for electric vehicle. So those are also it is also mandatory for electric vehicles. And other than that, we also have a manual service disconnect. We also have a manual service disconnect, MSD. This is the switch. This is kind of a plug connected in the battery pack. This is the type of connector connected in the battery pack. And whenever a service person or someone want to open the bonnet, open the inverter, open the converter, anything they want to do servicing activity, the first thing they have to do is remove this manual service disconnect. So basically this manual service disconnect is nothing but that a switch disconnects completely it disconnects the battery pack from the whole vehicle. Okay. So when before starting any servicing activity, people go and take this manual service disconnect. And the next component is the high voltage interlock circuit. You know about people, you know about youngsters, what we people do. We will not follow proper rules, proper statical regulations, proper methodology, right? So what we do, we will directly, sometimes what people do, without turning off the car, someone might directly go and touch the inverter. Without turning off the car, if I don't know about high voltage, I can directly go and touch the battery pack. So basically what they're doing for the purpose of safety of a layman, people have given a system called high voltage interlock circuit. So this interlock circuit is basically an additional safety. Other than this MSD, additional safety is provided in the interlock circuit. So whenever someone unknowingly opens an inverter, when opening itself, before he accesses the electronic part, by opening the lid, the cover of the inverter itself, he will disconnect the high voltage circuit. This is called high voltage interlock circuit. So by this also electric vehicles are made more and more safer. This is also another component of an electric vehicle. I hope people can understand. And why high rating fuses are required. When your electric vehicles are actually operating, there are more chances of pulse voltages, peak voltages and pulse currents possible. And you cannot determine how these pulse currents will be. Like they are very, very higher in thousands of ampere maybe. In such cases, your fuses are always recommended to be able to withstand this much high voltage and high current rating. But the problem is, it doesn't mean that these fuses will only withstand this one only for few milliseconds and few seconds. It doesn't mean that it will continuously take that. So this fuses only will take it up for a small amount of time only, right? So that's all about the components, guys. The last component of the session is the DC-DC converter. So the DC-DC converter is the additional component. So you use DC-DC converter basically to convert your high voltage from your battery into low voltage for your accessories, right? So to run your headlamp, tail lamp, water pump, say for example power steering pump, so like that, so many accessories are there in your car. So you want to run those accessories, so that you need a DC-DC converter. So don't think that electric vehicles are very simple to make. They also need so much of components. I hope you people got the point, right? I hope you people got a picture. This is how the DC-DC converter will look like. Here at the end of the today's session, let's have a small quiz. So currently we are now moving to the electric vehicle testing and standards. So how electric vehicles are being tested and what is the standard that applies to the electric vehicle, not only electric vehicle, even to the components, right? We'll just have a look at it. So why we need to look at this particular thing? Because there is a very big question mark among public. We are all public, right? So there's a very big question among the public that whether electric vehicles are safer, right? So that's a good question. Definitely, we have to answer that question. So that's the reason I am adding this also part of the session, so people should get aware that how electric vehicles are made safer. So maybe on the first day you would have come to know that there are so many safety components inside the vehicle that makes the electric vehicles safer. But still, if I say it will work, the contactor will operate when you do when I have a this, when I have a that, when during this condition it will work like this. When I say like this, no one will agree. I have to show that. I have to prove that, right? So for that, I have to have a testing process, and every government, every country has a certain regulation for that, developed for it. So today, what we are going to discuss in this part is what is meant by automotive homologation, and what is electric vehicle homologation is doing, and what is the safety requirements for electric vehicle manufacturers and component manufacturers, and how they are meeting it. Let us see. First, what is meant by automotive homologation? I told earlier that basically it is the process of certifying a vehicle. So today, if Maruti designs a new vehicle and they want to sell that vehicle from 2021 January, if Maruti Suzuki wants to sell a vehicle, what they have to do? They have to first do a prototype of that vehicle, and they have to bring that prototype to the testing agencies. So as I told, there are so many testing agencies in India. So in Chennai, we have a testing agency called GARC, Global Automotive Research Center. And in Mumbai, in Maharashtra, you have 2-3 testing agencies. I don't know why Maharashtra only specifically they are keeping too much testing agencies. That is a debatable topic, definitely. So in Pune itself, not even Maharashtra, even in one Pune itself, you have ARI, you have CART, you have VRDE, which is in very close from Pune also, Ahmednagar. So that is all 3 testing agencies are there in that region. And in the Gurgaon, we have one more testing agency called ICAT, International Center for Automotive Technology. Totally these 4 are the major testing agencies. And for tractors, we have a separate, for tractor testing, and all. We have a separate farm and machinery testing center is there. That is also in the north part. I believe it is in Madhya Pradesh somewhere. So automotive homologation means, so as a manufacturer, I have to create a prototype vehicle and I have to bring that prototype vehicle to the testing agency, and the testing agency will test each and every nook and corner of the vehicle, and they will check whether the vehicle is meeting certain regulations, and if the vehicle is not meeting the regulation, so it becomes mandatory basically not only for India. So even from India, if I want to export a vehicle to Europe or America, then I have to meet the regulations provided by Europe. Even I am manufacturing the vehicle in India. So to export a vehicle also, I need to follow the regulation. At the same time, to sell the vehicle internally inside India, I have to meet the regulations. That is very, very important. Right? Without getting the certificate, we call it as type approval certificate. So if you are going to start a new company, guys, if any one of you in future, if you are going to start a new company, a two-wheeler company, for example, then you have to apply, you have to make a prototype of the vehicle and you have to apply for certification. And after meeting all the regulatory measures, you have to get a certificate called type approval certificate. And after getting the type approval certificate, you have to use that for selling your vehicle. You have to give the type approval certificate to all the RTO of Tamil Nadu, RTO of Karnataka, and then the RTOs will transfer it to all district level RTOs. Then only your vehicle will be registered at the RTOs. I hope you can do that. And why it is being done? Why basically it is done? To meet the safety requirements. So basically people think today every news, online news I am seeing related to electric vehicle, I am telling that an electric vehicle catches fire. Electric vehicle, here an electric vehicle catches fire during charging, here an electric vehicle catches fire while driving. So those kind of many incidents happen, or you can say the media is actually focusing on that incidents basically. But if you look at the truth, the total number of fire accidents happening with vehicle, as an estimate, this is the data I have taken from EPA, Environmental Protection Agency of USA. In 2014 to 2016 itself, nearly 1,71,500 accidents, fire accidents have happened in USA with respect to crash. And most of them, they are telling that all these numbers are actually petrol, diesel, conventional vehicles, petrol, diesel and gas vehicles. Whereas it is just 2 to 3% of below that, you can say that it is the electric vehicles coming into the crash. Or you can say after crash there is a fire. But what people say, what people only look at these accidents. People only look at, identify only electric vehicles accident. But more than the electric vehicle accident, more than that, most of the electric vehicles have survived after the accident. But most of the passenger cars which have went to a higher accidents, higher speed accidents have not been, they are not been says from EPA. Able to survive, they have catch fire. That's what the data. But either it is an electric vehicle or it is a petrol diesel vehicle, we don't want them to catch fire. Obviously, yes, that is what the main agenda of doing homologation. They should not catch fire, right? So how to measure, how to avoid catching fire on the vehicle? That is what the companies are trying to improve themselves. So basically, when you look at an electric vehicle, these are the safety requirements for electric vehicles. These are the safety requirements for electric vehicle. So one is the shock protection. First one is the shock protection. So the vehicle should be able to be completely protected from, it should not give any shock to the passenger or any person who is touching the vehicle. Right? So that is the very important point of an electric vehicle testing. That is one of the requirements that people say. And unintended movement. Unintended movement. So suddenly, if I am parking my vehicle, I kept my vehicle parked in a parking lot somewhere or in a road, on the road. Suddenly there is no driver. Suddenly the vehicle is started moving. There is no ghost sitting inside the car, guys. Right? It's because of the malfunction happened in the powertrain. There is a vehicle movement unintentionally happened. Don't think it has not happened. It has happened in the past. Recently, very recently, Toyota. It's the best example. I don't mean anything mentioning the name because it came in the news also. Toyota very recently, they recalled lakhs of cars, lakhs of their hybrid Toyota Prius, because they came to know that for one of few customers, they came to know that unintentionally the vehicle is moving when in parked condition. So they came to know that there is a malfunction in the control part. There is a malfunction in the vehicle controller, and they immediately recalled all the vehicles of Toyota Prius, particular generation, particular 2014 or something, I believe, 2016, I believe, the year, maybe, I'm not very sure about it. So that particular year vehicle was completely recalled from the manufacturer, from the consumers to the dealers, to the service station, and they modified the control part. So unintentional vehicle movement is also something which is also very important that we have to see. And what else is there? Elimination and potential of thermal and explosive events. That is also a very important part. So whenever there is a crash or during any condition of the charging, or while charging the vehicle, or while vehicle is running, so I should not expect any, I should not have any explosive event on the vehicle. That is also part of the safety requirement of the vehicles. And RESS, so that means your battery pack. Generally in all the documents and all, we mention it as RESS, rechargeable energy storage system. Rechargeable energy storage system. Your battery packs are called as RWESS. So how the battery packs are installed? What is the IP protection I have to give? What is the integrity level? Whether the battery packs are properly mounted on your battery vehicle, or whether your vehicle, when your vehicle goes to bumps, whether your battery will fly out. So all these things are tested in the vehicle. We call it as integrity and the protection levels. And we also call it as RESS, rupture resistance and the toxic gases. So when there is an event, when I'm charging the vehicle, whether there will be any toxic gases coming out of the vehicle. If so, what is the level of the toxic gases? Whether that is harmful for the human. All these things are tested in the vehicle. And the final thing is low energy stranding. Means what? So while running on the road, suddenly I should not get information. Suddenly a vehicle is low charge and you cannot go further. So there should be an information to the driver. Regularly there should be information to the driver that what is the status of the charge level onto the driver. So all these things should be given to the driver. So whether the information regarding all these things are provided to the customer, the driver or the passenger, that is what been tested in the vehicles. So that the standards for testing the electric vehicles are being classified into two categories, guys. One is vehicle level standards, one is component level standard. In vehicle level, there are so many standards, and component level there are so many standards. So AIS, what is meant by AIS? AIS means automotive industry standards. Automotive industry standards. So AIS 38, 038, 0039, 040, 041, 049. These are all vehicle level testing standards. Vehicle level standards used to test the vehicles, electric vehicles in the market in India. These are all Indian standards basically. And these standards are developed not purely by India. These standards are all referenced from European standards. Basically, we copy, you can say we copy the European standard and we make changes as per our Indian climatic conditions. We make changes as per our Indian environmental conditions. We make the changes in the standard and we name it like this: AIS 38, 39, 40. In Europe, they call it as R100, R101, R102, like that in Europe. In USA, they call it as FMVSS, Federal Motor Vehicle Safety Standards, FMVSS standard 1, standard 2, like that. So in India, we name it as AIS standards. I hope you people can understand. So in component level, AIS 48 is the component level standard for battery pack. AIS 138, it is a standard for chargers. These are all component level standards. Let's talk about that one by one. We'll not go deeper, but we'll understand what these standards do. The AIS 38 is the standard. The AIS 38 standard talks about the functional safety of your electric vehicle. So we discussed many aspects. Do you remember, guys? I told what is meant by high voltage. I told you what is meant by high voltage, What is meant by high voltage orange color? Why the orange color is there? What is meant by IP rating? Everything is provided in detail in the standard called EIS 38. So since our company is actually working in very closely with these standards, we are aware of that. So this EIS 38 standard talks about the functional safety requirements for L, M, N category of vehicle. L category means two-wheeler and three-wheeler. M category means your cars. Basically, they come under the M category vehicle in India. And N category means trucks and buses, heavy vehicles. For all the vehicles, there are safety regulations provided in this standard. So the vehicles will be checked. So if I am a manufacturer, if I make a car, if I bring the car to ARAI, what they will do? They will check the standard. They will ask for the standard. They will check my IP rating, IPXXD. So we saw IP56, IP67. That is dust proof and waterproof. What is meant by IPXXD? What is meant by IPXXD and what is meant by IPXXB? These are all contact standards. Say for example, if I have a connector, whether my connector will go in, say for example, this connector in this area, look at this area zone, whether my finger will go inside this zone. That is called contact checking, contact verification. And that for that we call it as IPXXD and IPXXB. So how much they will take a probe like this. This is called a probe, like your finger, right? It will be size of a finger actually. The diameter will be like a size of your finger. So they will take the probe and they will check all the corners of the components, corners of the inverter, corners of the charger, corners of the DC-DC converter. All the corners will be verified by them and they will check whether the corners, these probes are going inside the corners, right? So that is called as the probe checking, the IP checking basically. And this standard only talks about the color coding. This standard only tells that any vehicle which is crossing this higher voltage level, with us staying in this higher voltage level, it is called as high voltage and we should give a color coding called orange color. And in the vehicle, hazard symbol should be, it is mandatory to keep the hazard symbol on the battery, on the inverter, on all the high voltage components, it is mandatory. If any manufacturer misses any one of these, their vehicle will be called as failed to meet the standard regulation. They will be called as failed to meet the regulation. So they will not be given approval. They cannot sell the vehicle in India. And one more thing I told you, remember isolation resistance. Do you guys remember I told isolation resistance? For every vehicle there will be a minimum isolation resistance. How it is calculated? How it is decided? For a car this much, for a truck this much isolation resistance. How it is decided? Depend upon the voltage that the vehicle is having. If the vehicle is having a DC system, say for example if it is a DC battery, and if it is a 450 volt battery, can you tell me what is the total isolation resistance minimum they should have? Minimum. Any people calculate? If it is a DC battery pack and the DC battery pack is having 450 volt supply, what is the isolation resistance they should have? So it should be multiplied by the total ohms. So they have mentioned in the standard that 100 ohms for every volt. 100 ohms of resistance is mandatory for every volt. So if I have 450 volt of supply, then 45,000 ohms or 45 kilo ohms is mandatory to have. So can you imagine, depending upon the voltage rating of your vehicle, the total amount of resistance that your component should have, minimum should be there, right? And if it is a AC component, then per volt ohm should be more. It is 500 ohms, 500 ohms per volt. And in addition to that, in addition to this, what they will check? They will also check the effect of water on your vehicle. When your vehicle is washed, when your electric vehicle is washed with a nozzle, when I am washing your electric vehicle in all directions, whether that will have an impact on the vehicle, that is also something they will check here. Unfortunately, what they check is very simple thing. Actually, in this standard EIS 38, they have a nozzle, and using this nozzle, they will spray water on the vehicle and they will check it. But these kind of Worst case conditions, they are not checking. What happens is, they have a test called, they have 3 tests basically in electric vehicle. Washing test, flooding test, heavy rainstorm test. Washing test and heavy rainstorm test, both are conducted using a nozzle like this. They will spray water using a nozzle. And flooding test is basically conducted on a water chamber. The vehicle will go into a track and the water will be like 10 centimeter in depth. Can you imagine, guys, 10 centimeter, how much depth it will be? 10 centimeter, can you imagine how much height it will be? Just a very small height. But do you have only 10 centimeter height water in our flood time? During our flood? No. So our floods are like in meters, right? They are in meters. So currently in India right now, we don't have the testing happening in the very higher level. It is only happening in the centimeter levels actually. So they just see how when the water splashes onto the inverter, whether when the water splashes onto the converter, when the water splashes onto the battery components, whether there will be any damage. So currently in India, they are only checking it limited. They are only checking it till 10 centimeter depth. I think you people will not accept it. But even in the European countries, they are keeping it quite higher. In European countries, they are checking it in a higher level actually. But why Indian agencies are not doing it? Because it will increase the cost of the battery car manufacturer. If they keep on if they put too much regulation on the vehicle, what they think is it will increase the cost of the vehicle. Manufacturers will not be able to meet that demand. Because of that, there is a compensation, you can say, some area there are compensation is happening. All the companies, they have their internal water bedding testing facility will be there. But at the end of the day, what they meet is actually the regulation. What the regulation says, that is what they try to meet. But even though the regulation said 10 centimeter, but the manufacturer, it depends upon the manufacturer, they check their maximum worst case possibilities also. Say some companies like Maruti Suzuki, Tata Motors, all these companies, they will not only test for 10 centimeter, they will test their vehicle for worst case situations also. Right? They will. It's up to their requirement. But in terms of standard, yes, standard is what's staying this only. And similarly, the next standard that we can see is AIS 39, AIS 039. So 039 talks about the electrical energy consumption of your vehicle. Electric load. How much watt hour? So today in our petrol diesel car, we call it as kilometer per liter. But you can see that in electric vehicles, we call it as watt hour per kilometer. That is what we should mention. In electric cars, we call it as watt hour per kilometer. So for every kilometer, how much watt hour your vehicle will consume. Right? That is very, very important. How much watt hour that your vehicle will consume for every kilometer. Right? Based on that only you determine whether the vehicle is efficient or not. If a vehicle has too much watt hour per kilometer, and you guys, have you seen the watt hour per kilometer of the Tesla truck, semi-truck, Tesla semi-truck, they recently shown one. It is around 2 watt hour per kilometer. 2 watt hour per kilometer. Can you imagine 2 watt hour per kilometer for a vehicle? So such a low energy consumption is possible. Today, all the companies are trying to bring down the watt hour per kilometer. And this is the standard, guys. AIS 39 is the testing standard. Using this testing standard, what they will do, they will take the vehicle onto a dynamometer like this. This is a dynamometer which is provided by a company called Suj, based out in Pune. Such Test Systems. I want to mention the company name as well. So that company provides test systems, chassis dynamometers for the testing agencies, even for manufacturers. So on this chassis dynamometer, it is basically a roller. It is basically a roller. On the roller, the vehicle will be rolling. And we know that our roads are not like rollers. Actually, the vehicles are tested on the rollers. I hope you people can understand why the ARE mileage is not it's not meeting the real-time mileage. I hope you people understood that reason. Because in ARAI, in testing agencies, they check the vehicle on the roller. Whereas our vehicles are not like rollers, especially during raining seasons and all, our vehicles are not like rollers, right? So this test is the one which tests the electrical energy consumption. So for example, when the manufacturers gives a vehicle for the testing, the manufacturer will be asked a question. Say for example, Tata Motors, when they come to the testing, the testing agency will ask Tata Motors, what is your watt hour per kilometer? They will give us some value, say for example 20 watt, 20, 30 watt hour per kilometer. And the testing agency will run the vehicle on the dynamometer, and they will check what they will do after running the vehicle. After running the vehicle, they will completely charge the vehicle again to full charge, and they will check after running certain kilometer what is the total consumption of watt it is consuming per kilometer. So the formula is C is equal to E by D. E means watt hour, total watt hour of energy, and D means distance covered in the dynamometer, in this dynamometer. It is the AIS 39 standard, so they follow that. If you want more detailed information, just download this standard and you can read it, and you can also reach us. So why I am showing here is you have to understand that energy consumption is being tested for the vehicle. And AIS 48 talks about method of measuring the range. So this standard measures the range of your vehicle. If any manufacturer, he will tell, so my vehicle will give 200 kilometer, my vehicle will give 1000 kilometer. We cannot blindly accept it. Jahir, the answer MIDC means Modified Indian Driving Cycle. Actually, we have a thing called a driving cycle. For example, if I travel from Bangalore to Chennai, during this 3 hours or 5 hours journey, I will have like so much time I will be accelerating. So many times there will be deceleration. Sometimes there will be traffic signals, so I have to be idle. So there will be a profile, right? So during my travel from Bangalore to Chennai, some percentage of time my vehicle will be in running acceleration time. Some percentage of time I will be braking. Some percentage of time I will be idle. Including all these things, if I bring it from Bangalore to Chennai, totally I took 5 hours. In this 5 hours, what is the total amount of acceleration? What is the total amount of deceleration? What is the total amount of idling? This is called as driving cycle. So for our whole country, for our whole India, we have something called driving cycle. For a whole India, we have a common system called driving cycle. Means what? If I develop a vehicle and if I run that vehicle in IDC cycle, it means I have run the vehicle all over India. It is like a commonization of the whole Indian's driving pattern. And GVW stands for the gross vehicle weight. Gross vehicle weight. It means total weight, including weight of the vehicle, including the passenger and the luggage compartment. It is everything included. It is called gross vehicle weight, GVW. So on this, when you are running the vehicle, when you are conducting this test, they will make sure that the vehicle is under GVW weight and the vehicle is running on the IDC cycle. So basically it's a programmed cycle. They will run it. They will automatically, they will run the vehicle, accelerate, decelerate, sudden braking, sudden acceleration, sudden braking, it will happen. I will explain you that by tomorrow. In the simulation part, I will explain you better. So when you look at the AIS 40, they measure the range of the vehicle. They measure the range of the vehicle. So this is the turbine, wind turbine. They keep the wind turbine in front of the vehicle and they will run the vehicle on the dynamometer. And they will check for one full charge how much kilometer the vehicle is running. And basically, in ARAI, in the testing agency, if they are getting 150 kilometer range, in real time they will get only 120, 125 only. I hope you can understand the difference. Why? Because the real time operating distance are different. Real time, the operating environment is different. Right? Chennai climate is not there in Bangalore. Bangalore climate is not there in Delhi. So the climate, environmental conditions are different. Road conditions are different in every part of the road in India. So ARAI mileage will not be the exact mileage that you will get it on road. So ARAI, they'll give you somewhere close to 150 kilometer, for example. The real time mileage will be like 120, 130 only. Because the driving cycle is not so much accurate. What we are using, the modified, actually the IDC was used initially. And later only people went for MIDC because of its lack of accuracy. But still IDC is used in some category of vehicle. So we use this standard AIS 40 to measure the range of your vehicle. We call it as AIS 40. And the next standard is called AIS 41, which measures the net power of your vehicle. Net power of your vehicle means what? What is the maximum power that your vehicle can deliver? 2 kilowatt, 3 kilowatt, 4 kilowatt, 5 kilowatt. If it is a car, then it can be like 30 kilowatt, 40 kilowatt, 100 kilowatt. So what is the maximum net power that your vehicle can deliver? That is also tested by the vehicle. And that is tested as per certain conditioning temperature also. That is also very important. A certain temperature is there that they have to consider. And 30 minutes power. What is meant by 30 minutes power? Any idea, guys? They already do a test called net power test. And there is one more test called 30 minutes power test. So 30 minutes power test means continuously the vehicle acceleration will be kept constant 30 minutes. 30 minutes, the vehicle should be able to give a constant power, a particular constant power. And that constant power will be, this detail will be provided by the manufacturer. So when the vehicle is running at a particular speed, what is the constant power that the vehicle can deliver for continuously for 30 minutes? Actually, what happens is the power will not be stable. Always it will be fluctuating. So what they will do is, for the 30 minutes continuously, they will monitor the power versus speed graph, and they will determine the average of the 30 minutes. That is called 30 minutes speed, because they want to understand whether the vehicle is able to sustain the power continuously. Because electric vehicles, when we had electric vehicles in the market before 2011 and all, at that time electric vehicles were very, very poor quality compared to today. They are far, far poor quality. If you accelerate too much, they will turn off, they will switch off actually. So they were not properly tested basically. So the testing agencies brought down standards like this, 30 minutes power testing, where continuously the electric vehicle should be able to provide certain power output. That is tested there. And we also have a test called starting gradability test. Starting gradability test. In this test, what they will do? They will check whether the vehicle, whether the electric vehicle is able to start on the gradient. So we used to do right in RTO. We used to stop the vehicle, we switch off the car, and once again we start the car and move. Same way they do the test called starting gradability. So they go take the vehicle to the grade, they will switch off the car, they will turn on the car, and they will start the car from the gradability itself. And at that time the minimum SOC should be 60%. SOC means state of charge, you know. And for electric vehicle two-wheelers, the angle is 3.81 degree minimum it should be able to climb. And for other electric vehicles, passenger car and other electric vehicles, even two-wheeler only, if it is power output of the two-wheelers below 2000 watt, it is given limited. But any other vehicle which is having electric vehicles, they should be able to climb minimum 7 degree. Minimum gradability should be 7 degree. So the standard is called AIS 003, which talks about the starting gradability. And you are seeing some R numbers. I understand you might think what is the R numbers are nothing but the European standards. From that European standard only, they have referred to this AIS standards. And we also have a test called measurement of pass by noise test, IS 3028. Measurement of pass by noise. So using the test, what they will do? They will keep some microphones on both the sides of the vehicle, and they will run the vehicle in this track, and they will check what is the total noise developed by the vehicle while running at the peak power. So here they measure the noise that is generated by the vehicle in terms of hertz. So they measure the noise, and there is a limitation specified in the vehicles, say 75 decibel. They measure it in the decibels, and they can compare with the standard regulations. They will compare that with the what do you say? Even for conventional vehicles also it is there. This test is there. Even in today's petrol diesel cars also you have the pass by noise test. Similarly, electric vehicles also pass by noise test is there. So you have to run the vehicle at somewhere close to like 50 km per hour or 75% of their maximum design speed. So if the vehicle has a maximum top speed of 100 km per hour, then this test will be considered when will be conducted at 75 kmph. EMI and EMC test. So we call it a standard called AIS 004. And guys, I have experienced the EMI EMC in front of my eyes many times. I don't know how many people know the seriousness of this EMI EMC, but these EMI EMC problems, I can give you some examples. What are these EMI EMC problems? Maybe when you are driving your car on road, suddenly when you are coming under a high voltage cable, suddenly if you are using a radio in your car, FM or your car, your FM will be fluctuating, you know, like there will be a disturbance in your FM. Similarly, whenever your vehicle is crossing, maybe like, you know, depend upon, whenever, for example, in some of the cases, in some of the accidents happened in India, airbag was not opened during that accident. And when they investigated that, everything was fine. What happened is, during the operation of the airbag, there was a malfunctioning happened. That means there was a wrong signal given to the airbag during the crash, a malfunction caused by EMI EMC. Similarly, I recently had an experience with one electric vehicle. When we were testing that electric vehicle at one of the testing agency, we came to know that when we press the horn of the electric vehicle, suddenly the acceleration of my vehicle changes. So there is a relationship between the horn, the signals that is going for the horn, and there is a disturbance happening on the motor controller because of that. So EMI EMC problems are very, very critical. And as electric vehicles have almost all our electrical components, what happens is there are more criticality comes into picture on electric EMI EMC. So EMI EMC tests are becoming very, very challenging in the coming days for EV manufacturers. This is an example of an EV EMI EMC test chamber. We call it as semi-anechoic chambers. So these are basically the Faraday gauges, like Faraday cage. So they will not allow any disturbances coming out from the outside environment, and they will not allow the signals present in here inside to go outside. So basically it's a semi-anechoic chamber. If I keep it even below also, it is called a full anechoic chamber. This kind of materials. So we conduct these following tests on the vehicles, on the electric vehicles. So when you take an electric vehicle, two things are important. One is, I should not do any radiation. My vehicle, say if I am a motor controller, if I am an inverter, if I am a charger, if I am a DC-DC converter, whatever be the, I am an electrical, I am a E&E component basically. I am an E&E component. So the E&E component have certain requirements. First requirement is, it should not give any unwanted radiation. Second requirement is, the component should be having proper immunity. Say for example, if I am developing a motor controller, the motor controller should be having the component. Say for example, I am keeping the motor controller and get affected by the other, I am keeping the battery pack, both are very close together. So because of the radiations coming, for example, if there are some radiations coming from the battery pack, I should not get effect on the motor controller. Similarly, because of the radiation coming from the motor controller, I should not have an effect on the battery pack. So both are very, very important because the battery pack has the BMS. So BMS is a very critical component. Everyone knows that. So end of the day, any E&E component in your electric vehicle should have two characteristics. One is, it should not do any radiation, unwanted radiation of electromagnetic noise. At the same time, any noise that is surrounding you, the component should not get disturbed from that. And these tests are conducted as per the AIS 004. This AIS 004 standard tells how the test is conducted, how the test should be conducted. And the tests are conducted at two levels. One is vehicle level and one is electrical and electronic sub-assembly level. What does it mean by? What does it mean by, guys? We have vehicle level testing. We have electronic sub-assembly level testing. That means what? The whole vehicle will be taken and kept inside this chamber, and the radiation will be applied on the vehicle through a transmitter. And the vehicle, all the electric vehicle components, including your headlamp, tail lamp, windshield wiper, all your horn, each and every electric vehicle component, electrical component, not electric vehicle, electrical component. Because this test is conducted even for petrol diesel vehicle also. It is mandatory. Even for petrol diesel vehicles today, there are so much of sensors, so much of ECU is there, right? Because of that, it is mandatory for petrol diesel vehicles also. But for electric vehicles, it is more challenging because there are so much additional for required for the electric vehicles. So what happens is here, the EMI EMC's testing. So what happened? They will do it in the vehicle level as well. And what they will do immediately after that, they will remove the inverter. They will ask the manufacturer to provide the inverter, to provide the battery pack, to provide the converter, the onboard charger, all those components separately on component level, and they will check. They will do the same check. They will do the same check on the component level also. They will apply the radiation on the component, and they will check whether any radiations are coming from the component. So radiated broadband check, radiated narrowband, immunity check, and radiation check on assembly level, like a battery, motor, all these components connected, how it will look like, not on the vehicle but in the assembly level. So like this, they do the checking of the electromagnetic radiation, and these are the limits they are provided for the vehicles. On the broadband check, broadband, what is the limit? On the narrowband testing, what is the limit? On the immunity test, what is the limit? Say beginners who are all very beginners to this electrical vehicle, just understand there is a EMI EMC test is conducted. No need to go and deep understand that, but understand that EMI EMC tests are conducted at both vehicle level and component level, because both the levels there are problems will come. So how to avoid these problems? How to determine whether I need to whether my component needs a test or not, EMI EMC test or not. So for that, they have given a guideline in the standard. How to select, how to determine whether this particular component needs EMI EMC test or not. They have given a guideline in the standard. So if your vehicle is meeting some critical components, say immunity relevant functions, for example, if some of your component meets the direct control of your vehicle. So can you guys tell me what are all the components that is used to direct control of your vehicle? Who is controlling your vehicle basically on the road? Driver. Pedal, decelerator pedal, your gear actuation systems. All these are containing the direct control of the vehicle. So these systems will be tested. For these systems, it is mandatory. And protection of driver, passenger, and other road user. Can you give any example? What are all the systems that protects the driver, passenger during a crash or anything? Any example? Airbag, seat belt, all these components, it is mandatory to have to get EMI EMC test. And systems when disturbed cause confusion to the driver or road users. So what this, can you tell which component? Systems when disturbed cause confusion to the driver or other road users. Can you tell me any example? Indicators. So if I put left indicator, because of EMI EMC problem, suddenly right indicator is working. Can you imagine what will happen? Right? So it is a dangerous situation, especially in highways. If I am running at a very high speed in a highway, I am putting a left indicator, but because of EMI EMC problem inside the indicator, it is putting right indicator. Can you imagine the disaster which can happen? Possible. So that is why it is mandatory for those components also to test EMI, and even vehicle database functionality. So all the ECUs, you have hundreds of ECUs sitting in your vehicle. Say you have an engine ECU, you have an ABS, you have a separate electronic control unit. For airbag, you have a separate electronic control unit. For fuel control, you have a separate unit. So every So the ECUs has to control the CAN communication is there. So during the CAN communication, there might be disturbance in the signals because of the electromagnetic radiations that are possible. So this EMC signal, EMC test, make sure that all the communications are properly working. And we call it as, we also have a standard called ISO 26262, which talks about the functional safety standards, functional safety of automobiles. So if you are an electrical electronics guy, most of the time you will be working in future, you will be getting a job in this area only, ISO 26262 standard and related firmwares. So how to address this EMI? So many people are following different methodologies. So we can do proper shielding. I have shown you the shielding done in the high voltage cable. So proper shielding is one methodology that can avoid the EMI issues. And enclosure design, proper enclosure design is very, very important. When I have a DC-DC converter, when I have a motor controller, the enclosure should be properly designed and the proper component integration should be there. So you have so many power electronic components are there. So component integration should be very, very important, and ensure good wiring harness practices. That is what is missing. Other than reputed OEMs today, many startup companies, they are not giving importance to the wiring harness. They are like messing the wiring. They're not properly following the standard wiring harness practices. And when we do this, obviously you will have impact on the EMI EMC. Because if I have a power cable and I have a signal cable flowing together, then obviously I will have a disturbance on the signals on the signal cable. So the best wiring harness practices should be followed by the manufacturers. And more than that, in addition to all these things, there are today special materials used in the industry. Insulation materials are used in the industry. So if still there are some EMI issues are there, you can go for insulation materials, special materials for the components, coatings, special EMI EMC coatings are available today in the market. They can apply these coatings on the components and the vehicle. The next part is about the battery testing. How the batteries are being tested. So we saw that different constructions were there, cylindrical, prismatic, pouch, different constructions are there. So we use a standard called AIS 48. Currently, the standard which is used by the Indian agencies is AIS 48. So this AIS 48, what they do? They do 5 tests for the battery. What are the 5 tests? Short circuit test, overcharge test, shock test, vibration test, and nail penetration test. Short circuit test, they just do short circuit on the battery and they will see what will happen. The requirement is for all the tests, the criteria is after checking the battery, after conducting this test, the battery should not have any physical damage. There should not be any fire or any explosion. No components of the battery cannot melt. So can you guys understand that these are the conditions, passing criteria for the battery, for the automobiles. So totally 5 tests are there. Short circuit test. Overcharge means like they will overcharge the battery, like they will apply the charging continuously. When you overcharge the battery, what will happen? They will see. So overcharge test, make sure that after overcharging, what will happen? Nothing should happen. As per the AIS 48 standard, they tell that when I do overcharging of a cell, the cell should the cell should not have any of these problems. Maybe the cells can reduce its performance when I do overcharging. That too, there is a limit for that. That is specified in the standard AIS 48. And the shock test. Shock test means not an electrical shock, it's a mechanical shock. So they will lift the battery to a certain height and they will drop the battery. Right? They will drop the battery from certain height at a certain G force will be applied on the battery. And after that, they will check what is the deterioration. What is the deterioration of the battery after this check? They will check how much, say for example, they will fully charge the battery. After the test is conducted, they will check how much capacity is remaining. When they check it, there should not be loss of capacity more than 10%. That is the condition. At the same time, there should not be any physical damage to the battery. This test is mandatory for all 2-wheeler, 3-wheeler, passenger car, bus, for all manufacturers, it is mandatory. And the 4th test is vibration test.
where they will keep the battery pack onto a vibrating chamber. They will keep on vibrating the battery on all three axes, x-axis, y-axis, z-axis, and they will vibrate the battery and they will check how the vehicle is, how the battery is responding. And the final one is the nail penetration test. They will take a sharp nail and puncture the battery. They will puncture the battery, and after doing that, they will check what is happening. Nothing should happen. Nothing should happen. As per the nail penetration test, the battery should not have any melting. They can have physical damage, yes, because holes will form. Right? When you penetrate it, there will be a hole formed, but there should not be any fire explosion and no melting should happen. And I have seen some manufacturers cells flying inside the lab. They will fly inside the lab initially when they were starting the test and all. And now we have a proper chambers for that, for conducting the nail penetration test. So in India, only these 5 tests are conducted: short circuit, overcharge, shock, vibration, nail currently. But if you take European countries and America, there are totally 15 tests are conducted. 15 tests are conducted. Thermal overheating, bringing to the cold temperature, vehicle bringing to the cold temperatures, overcharging at extreme temperature, fire test, directly burning, throwing some fuel on the battery and burning the battery. What is happening in the battery? That level, the test is there. Currently, India is not having the test, but don't think it will be there. The same will be applicable next year. Very soon, you will see a change. A new standard is coming from next year in India also. That is nothing but the replica of the same European standard. So from next year, that is the standard number is AIS 153. So new standard is coming, a new revised standard is coming in the electric vehicle battery. So from next year, it will be followed by all the manufacturers. It should be followed by all the manufacturers. Currently, very recently, they put the standard in online also. They are asking for feedback from general public. What is the feedback you want? So they have asked the feedback also. So right now we have only 5 tests. Right now the electric vehicle batteries are not very safe, if you ask me personally. That is why even I have not purchased electric vehicle, because I know these standards and regulations, right? I know currently the battery packs which we use in India are not 100%. 100% they are not safe, because they are not being tested and as per the regulation provided by European market. So I was waiting for this regulation change, and as I expected, the change is happening now. Next year, it has been already launched in the draft. If you go to the Ministry of, you can see the draft standard published there in the Ministry of Road Transport website. So I expect this standard to be published, will become mandatory. So next year, I think the new standards will be applied, where you have the additional tests conducted. Okay, but currently it is only the 5 tests which is mentioned here. And the final one, crash safety. Whether my electric vehicles are safer towards crash. So crash safety, when you talk about crash safety, there are different standards. AIS 98 is for the crash safety for electric for vehicles, for passenger. When I have an electric vehicle have a crash, what should happen in an electric vehicle? So we know that electric vehicles have a voltage of 300-400 voltage, especially passenger car. So the requirement of an electric vehicle is that immediately after a crash, immediately after an accident, within 280 milliseconds, the airbag should operate. Not 280 milliseconds. Basically, totally it takes the signal to transfer from airbag to the sensor to the controller. It takes totally 40 milliseconds, and the operation another 50, so totally 280 milliseconds. And you can see that at 1180 milliseconds, the voltage of your battery should come down. That means what? The moment your accident happens, immediately, you know the contactors, the battery contactors, the main relays, the main contactors will immediately open. When they immediately open, that means the circuit gets completely open. What happens is the voltage, your battery will be like at the voltage of 300-400 voltage. And the moment you remove the contact, moment your contactor gets open, your voltage will stop coming down. How quickly it should come down, that is very important. That is what the standard says. So the electric vehicles are tested that how quick the voltage gets down to below 60 voltage. Below 60 voltage.
So that's a lithium-ion cell, and I'm going to show you what would be the consequence if I overcharge the cell. Bulging actually. Now you can see that. Can you see now?
Yes,
Yeah.
the cell is visibly bulging. I
Yeah,
can
the
see
cell
it.
is visibly bulging.
Yes, because according to our checks, we're getting very close to overcharging it.
Yeah. Now it's time for us to move back. Move back.
So I see a bit of smoke. Oh my goodness.
Can you come? Yeah.
Imagine this multiplied many times when it's all in a pack.
When you pass a current, and you notice about a 10-degree rise in temperature during the whole charging process from an unreliable source, while the temperature does not rise beyond 3 degrees centigrade for this particular cell obtained from a reliable battery manufacturer.
Okay, so what's the worst that can happen?
Every time cell warms up, you are evaporating the liquid electrolyte into gas, and the local pressure build up, and it leads to so-called,
An explosion.
explosion. The other possible cause could be inappropriate charger. That's very important. You must get the same charger which is meant for this particular pack, preferably from the same supplier.
LG Chem manufactures the world's finest batteries using a large-scale precision system. Let's have a look at the production process. First, raw materials are combined in a mixing process. The electrode material is coated onto copper and aluminum foil for electric flow. Next is assembly. Here, a separator and electrode are joined together. The joined cell is then stacked on an LG patented safety reinforced separator to be folded. This unique stack and folding technology prevents twisting of the battery due to internal stress. This unrivaled technology is LG Chem's worldwide first and best patented technology. The lead tabs are attached to the folded cells. The assembly process is completed after putting electrolytes into the cells. Those cells are activated through charge and discharge in the formation process. Lastly, through high-tech automation and robotics, these will become batteries. LG Chem will establish itself firmly as a global leader by attaining 25% global market share. The global leader, LG Chem.
So today what we are going to discuss, it is going to be on energy storage system design. So basically we have we have discussed about the motors and inverters in the last 2 days session, right? So we have talked about the motor and the inverter. So end of the day, who is consuming the motor and the inverter? The motor is consuming the power. So there should be someone who can give that power. So it is the battery pack in the electric vehicle, right? So in your passenger petrol diesel car, it is your fuel tank that gives the source of power, and basically in your battery pack, in your electric vehicle, it is your battery pack. So let's understand how this battery pack is going to influence the electric vehicle. What are all the different types of battery packs are there? And I will try to make you aware on all the very important parameters that is very important when selecting a battery pack, how to select a battery pack, right? And regarding the sizing of battery pack also, the fifth day will be this correct area. So fifth day with the motor sizing, just some few steps are there for battery sizing. I'll just add that in the fifth day. Okay, but today we'll talk about the different battery technologies and the suitability for different applications. So when you talk about the batteries, so today the lithium batteries are there in the market. So you might be knowing that the lithium batteries today in our mobile phone, we have the lithium batteries. And in terms of electric vehicle, what happens is you need some batteries. So till now, currently, which battery actually we are using in our conventional vehicle, petrol diesel vehicle? What is the battery technology we use? Lead acid battery, right? So currently we are all using lead acid batteries in our vehicle, in our petrol diesel vehicle for the accessories, basically the headlamp, tail lamp and all the accessories, right? To run the accessories. So what happens is this lead acid battery, what is the problem? Why can't the people directly use the lead acid battery in the, they can expand the lead acid battery itself, right? So why they are going for some other new technology? First we have to understand that problem, so that it will give you better idea on the upcoming part. So the lead acid battery, when I take a lead acid battery, the problems are like multiple parameters are there when we have to compare a battery. So we will talk about that now. So when you look at the overall battery technology today for the electric vehicles, there are three types of construction they are looking at. Three types of cell construction. One is cylindrical cell construction, another one is the prismatic cell construction, and another one is the pouch type cell construction. All the three are having some positive and negative factors that depending upon the particular company, they will decide it what they want to do. Say for example, Tesla is always working on, Tesla focuses on the cylindrical cells. Whereas companies like, for example, BMW i3, for example, if you take BMW, they focus on prismatic, this one. And when I take Chevrolet, they go for something like pouch, this one. All the three are having some positive and negative, right? Say this particularly, what happens, why Tesla initially went for this, they are actually using this cylindrical cells. It's because their flexibility in the control of temperature. So what happens is, when the Tesla car is being charged with a fast charger, or when the car is running at a very high performance, in all the cases, what happens is the temperature control is very, very important. How the battery pack temperature or the battery cell temperature is kept in a particular range, that is very, very important. And the purpose that Tesla selects this cylindrical cell is because in the cylindrical cells, the maintain the temperature is very good compared to the other types of cells. And because of that, that is one of the reasons that Tesla says that they are going for the cylindrical cells. And even they were able to nearly, you can say the Tesla Model S, it has something close to 4,000 cells like this. Nearly 4,000 cells are there like this. And what else about these companies? These companies, what they think? They think that if I use these kind of cylindrical cell, the manufacturing duration, total duration for manufacturing I will not be able to quickly build the car. That is what these people think. So basically, these are all conventional car companies, I would say. Tesla is quite different. They are a quite different company, and these companies are conventional manufacturers. They have been there for the automobile industry for 100+ years. BMW and Chevrolet, all these companies are there for the very past 100 years. So they follow that conventional. So what they think is how much vehicles I can manufacture per hour, per second, even per minute, how many cells I can make. That is the way they look at it, right? So in that case, like what they do in the prismatic is they join some 2-3 cells together and they form one prismatic cell. And here in this case, one pouch cell contains like one particular cell. This is one particular cell having one terminal, positive and negative terminal. So depending upon the type of manufacturing, depending upon the total manufacturing time that the vehicle takes, all factors decide, even the flexibility. So if I have the cylindrical cell, what I will is I have the flexibility to shape my battery pack, especially two-wheelers. In India today, most of the two-wheeler companies, they go for the cylindrical cells only, because in two-wheeler, there is a limited space. So whatever the space, I have to, I have to change the shape of my battery according to that. So most of the people go for cylindrical cells in order to modify or accommodate their battery pack according to their shape available there, space available there. So some people go for cylindrical, some people go for prismatic, and some go for the pouch type. So when you talk about the batteries current, I just want to talk about which is having scope for the next coming years. Right now on the lead acid batteries, guys, there is a very good scope for the lead acid battery. You remember, especially the research scholars who are attending here, we know that wherever the problem is there, then only there is a scope for research. So lead acid battery, right now there's a huge problem that it should meet all the requirements of lithium batteries. That means whatever lithium batteries are able to do, that acid batteries also should be able to do. That is the requirement in the industry today, right? So what happens is when you talk about the lead acid battery, you know about the reactions. Lead acid batteries we have been using for so many years. So we have the lead and lead oxide, and you have the sulfuric acid sitting inside as an electrolyte. So the lead acid battery, what happens is basically you have the lead oxide and the sulfuric acid. So even though it has lead and all these issues are there, still so many years we have been using the lead acid battery. Until now, we have not seen major issues from the lead acid battery. And it does not ask you any special controller, special BMS, all this, nothing, no complex systems are there in lead acid batteries. That is the reason still I am a supporter of lead acid battery actually. If you ask, especially on the Indian case scenario, if you ask which battery is good for, India like country, initially at this point of time, right now, yes, it is not possible for all the vehicles to have lead acid batteries. There are so many disadvantages there, but still lot of work is going on. All the companies like Tata, Mahindra, all the companies have their separate team working on lead acid batteries, and they are improving the lead acid batteries in terms of weight, in terms of energy density. Even there are some central government organizations in India who are all working on the lead acid battery side, right? So at least if you are not directly completely coming out of the lead acid battery, what people can do is they can do hybrid batteries where say how the hybrid vehicles are working. Similarly, people are currently working, they are developing some battery called hybrid battery, where it will be like partly it will be lead acid battery and partly it will be a lithium ion battery and partly supercapacitors. So the combination of these things in different zones, right? So while starting, I need more current, I need more acceleration, so people go for supercapacitors. So after the vehicle is started, vehicle is moving, then I don't need very huge amount of current, then I will go for the conventional battery. So like that, depending upon the different situation, people can switch from one battery to another battery. I believe that will be the coming future. So people will focus on the hybrid batteries, or right now the supercapacitors prices are coming down, and because of that, you will definitely see a change in the market. But when you talk about lithium ion battery, yes, currently for the next 20 years, you don't have option that you have to go for a lithium ion battery only. Even the manufacturers, they cannot fluctuate from one battery to another battery like every day. They cannot do that. As a manufacturer, you think about it. As a manufacturer, they want a solid solution. For the next 20 years, they should not move out of that solution. That's how they think actually, right? So when you talk about the lithium ion battery, you have these two components. You have a cathode collector that is made up of aluminum, and you have an anode current collector which is made up of a copper. And basically the cathode is coated with lithium metal oxide. It can be a sum of a metal oxide, any metal oxide. I'll give an example here. And the anode is coated with carbon, graphite carbon, and you have a separator. So what happens is when you do charging and discharging, so these ions cross through and you get the electricity generated. That means, say, what happens is like the negative electrons cross through the electrodes. And say this is an example of a battery. This is an example of a lithium ion battery. So in this case, it is a lithium ferrophosphate battery. It is nothing but phosphate. The ferrophosphate is being coated on the positive electrode, the aluminum foil, and the negative, the negative electrode is being coated with the copper. It's a copper foil basically, and it is coated with carbon, right? So this is a lithium ferrophosphate battery and one of the safest battery, right? So we'll discuss more about the lithium batteries, because as per the current situation, the market is there. your scope and everything is currently in this area only. That is why we are discussing about that. So when you talk about battery packs, when you talk about battery energy, these are very, very important parameters, guys. Understand. When you talk about different cells like lead acid battery, nickel cadmium, nickel metal hydride, lithium ion, these are the mainly used automotive batteries, out of which nickel metal hydride is mainly used by Toyota. Actually, Toyota is one of the company, and Toyota and Hyundai, they are the two companies which preferably they used initially nickel metal hydride, because nickel metal hydride batteries are, compared to lithium ion batteries, they don't need very high level, highly sophisticated battery management systems and all. And lead acid batteries, yes, they have many advantages and disadvantages as well equally. And you have lithium ion batteries. So when you compare, let us see how it is compared. Say you look at the cell voltage. Per cell voltage is very, very important. How much voltage per cell can give? That is very, very important. That decides you totally how many cells you need for the battery pack. Correct? If I need 100 voltage, to make a battery pack, so if it is a lead acid battery, I have to make how many cells? 50 cells in series. Depending upon how many volt that your battery is having, your number of cells will change, right? So more voltage is required. That is what is needed. And if you compare that, all the batteries, lithium ion batteries are able to provide up to 4 volt, 4.2 volt. When you fully charge the cell, a lithium ion cell can give you up to 4.2 volt per cell, right? Whereas in the case of lead acid battery, you know this, it is well known that it is 2 volt. And in case of lithium, nickel cadmium and nickel metal hydride, it is somewhere close to 1.2. It's very lesser. That means what? You have to add more number of cells if it is nickel metal hydride. And specific energy and energy density, these are very, very important. How much watt hour of energy is possible in the battery per kilogram? That is very important, right? If this is very lesser, then your weight of your battery will be heavier. Say for every kilogram, how much watt hour of energy will be there? So when you compare this term with lead acid battery, nickel cadmium and lithium ion gives 100 to 300 watt hour per kilogram. Whereas lead acid battery just gives 30 to 40 watt hour per kilogram. So per kilogram, that is the total watt hour that you can have, that you can store. That is the problem. This is also one reason that people go for lithium ion battery. And moreover, the very important thing is the power density. So energy is the rate, and the power is basically the total watt of power that is available. In that way, lithium ions are far, far better compared to the other 3 batteries. Not with supercapacitor, but with these 3 batteries, this is the best. And when you talk about the usable capacity, this is much more important. So the depth of discharge, how much discharge you can make on the battery. In that sense also, lithium ion batteries are more than 80% usable capacity is there. Usable capacity is more than 80%. So you can use nearly more than 80% of the battery for every time you use it. And not only the usable capacity, that means the discharge side, even the charging efficiency also. When you charge the battery, you generally see our cars and all. When you charge our normal mobile phone also, your charger gets heated. So when your charger gets heated, what it means? It is loss. There is a loss of power in your charger because of in terms of heat. So similarly, in your electric vehicle also, the batteries can, if the batteries are not having good charging efficiency, so they will increase the losses. So when you look at that perspective also, lithium ion batteries have more than 90%, 90-95% depending upon the chemistry, 90-95% charging efficiency is higher. So these are all the factors, guys. So I hope you got to understand that why people are now focusing on lithium ion batteries, right? And the temperature range where it works, how it can work. So in that way, you have, like when you talk about the temperature, that is a very important characteristic when you are selecting a battery, and especially when you are making a car for like a European country, when you're making a car for India, so the battery pack should be able to work in both the ranges basically. And moreover, on this, the cycle life is also very important. Cycle life. So what is the cycle life? Any idea, participants? Yeah. So if I call one cycle life means one full discharge and full charging. This we call it as one cycle. So basically, if I do the same for 365 days, then for 1 year it is 365 cycles, right? So when I talk about lead acid batteries, the lead acid batteries have nearly 200 to 400 life cycles. And when you talk about the lithium ion batteries, they have a minimum, they are having somewhere close to 1500 to 2000 life cycles. And when you talk about specific cell chemistries that we are going to discuss in the next slide, as the cell chemistry changes, say ferrophosphate, NMC, and different cell chemistries are there in lithium batteries. So depending upon the cell chemistry, even up to 10,000 life cycles are also possible. There are some batteries with 10,000 life cycles also. Okay, there is a company in Canada which has a battery with 8,000, 10,000 life cycles, right? So even the lithium ion batteries, the life cycle is very, very important because that determines the warranty of the battery pack, right? So if Tata is giving 10 years warranty to their battery pack and motor, that means that they are very sure that their battery packs will work for such a long time, right? And moreover, end of the day, what happens is we also have multiple factors. So they call it as memory effect. So memory effect in the sense, like end of the day, the memory effect and self-discharge capability, self-discharge. So if you keep, if you keep the battery without using for so many time, say 1 month, if you are not using your car, if you are not using your electric vehicle, right, you went somewhere outside. After 1 month or even say imagine 3 months, after 3 months you are coming back. What will happen to my battery? So if it is a lead acid battery, you know what will happen. What will happen if it is a lead acid battery? Yes, it completely becomes dead. So it becomes completely dead. The battery becomes completely dead, and we came to know that we have to charge it and bring it back to the life. So what happens because of this? What happens? The self-discharge capability is also one of the parameter very important to select when you are selecting a battery. Right? In that case, look at the self-discharge capability. It is just 2 to 3% of the charge will be discharged from the battery for every month. And when you talk about nickel metal hydride battery, this is quite very higher. That is why that some of the companies, they don't prefer the nickel metal hydride batteries, because the overall self-discharge of the batteries are basically higher. Right? And when you talk about the memory effect, that is also one of the factor. Memory effect, what happens is like the battery stays in a lower capacity, right? The battery goes to a lower capacity and the battery stays there in that lower capacity. So people used to call it as, like memory effect for the battery terms. And end of the day, the final thing, as for a country like India, what we need? Robustness. So when you talk about robustness, that is something missing in lithium battery. But when you talk about lead acid battery, they are definitely robust enough to work in such a very harsh environments. And when you talk about lithium ion battery, yes, definitely we need a controller, we need a special battery management system controller to maintain the battery under the threshold values. Overcurrent, prevent overcurrent, prevent the batteries from over voltage, overcurrent, and all this scenario. Right? So the robustness in that case, the robustness scenario, lithium ion batteries are actually, they need a dedicated BMS, a battery management system controller. Right? I hope people got a clear understanding on different batteries, and this is the reason why people currently focus on this particular battery, lithium ion. And when you go inside lithium ion, there are so many chemistries are there. Lithium cobalt oxide is there, nickel cobalt aluminum is there, lithium ferrophosphate, and nickel cobalt manganese is there, lithium titanate is there, lithium manganese spinel, we call it as lithium manganese oxide batteries are there. So many cell chemistries are there inside lithium ion battery, and all these cell chemistries are not suitable for electric vehicles, right? As we know, electric vehicles are very dynamic, so their requirement is very dynamic. Suddenly the driver will accelerate, suddenly they will overtake the vehicle, so suddenly they expect a huge amount of current from the battery pack. So because of that, what happens? Different cell chemistries have different characteristics. So however, as I mentioned in the previous slide, these are all the parameters that we have to compare with battery to battery. But these are the parameters that you have to compare inside the chemistries itself. Like when you compare lithium cobalt with the NCM, when you compare lithium ferrophosphate with other battery, these are the parameters that you have to look into. The first one is the cell level energy density. In terms of energy density, so which battery is able to store more energy? Can you people identify from the table which is the worst and which is the best? Okay, could you tell me from this table? So LCO is having the higher specific energy, and which is the lowest one? NCM and LFP, both these chemistries have lower specific energy, right? Even though they are having lower specific energy, But look at the other parameter. Let's talk about this. Let's talk about the C rating. C rating means like it is the cap. Right now we will not discuss detail about C rating. I will come to the next slide. But right now understand that C rating means it is the capability of the battery to provide huge amount of current in a very short time, very quickly. Okay, like kindly understand in such a way how quickly it is able to provide huge amount of current. That capability. So look at that capability, which is having the highest capability of providing huge current in a shorter time. Which battery chemistry? You guys compare that, right? So see, LFP was not good in specific energy, but you look at the power rating, it is very good. But look about the other parameters. Look at the nominal potential, the cell voltage, per cell voltage, which is having the highest. That means nominal cell voltage, per cell voltage.
LMO.
So the lithium manganese oxide. So every company they select certain particular batteries because there is some reason behind it, right? I think this slide, this will give you a better picture. Just look at this picture, guys, everyone. So here I have completely compared. We are taking a comparison of 5 different chemistries: NCA, NMC. NCA batteries are used by Tesla. NMC and LFP. These both are used by most of the Indian companies, Indian electric vehicle manufacturers. LMO is manufactured by it is being used by Mahindra in India because it is very cheaper actually. And LTO is not used by automotive manufacturers as per us now. Okay, you compare 5 reasons. Right now there are 6 parameters we are compared. Let's look at the cost. All the participants, let's look at the cost. Could you tell me which is the cheapest battery in all the 5?
It's LTO.
Cheapest. No, it means if the web is like this, that means worst case. If it is here, it means best. So look at, say for example, which batteries. I think LFP is having the higher point, right? So this is the best. That means cost is lower. So when the web is to the higher area, that means it is best criteria, and it is coming down and down. It means going to the worst criteria. Okay, that is how you have to understand the web spider diagrams basically. So now tell me in terms of cost, which is very cheaper. Okay, LFP is cheaper, NMC is cheaper, and LMO is also cheaper. And very high cost is titanate, lithium titanate oxide. And now you know why Indians are using this. Yes. Now you understand why Indian companies are using these 2 batteries specifically. One of the reason. And second thing, lifespan. Look at the lifespan. Which battery is having highest lifespan and which is having the lowest lifespan?
NCA, LTO, and LFP.
NCA and LFP, LTO. These 3 batteries are having highest lifetime, and LMO is having very less lifetime. So now tell me, which battery do you think it meets almost all the criteria in a meaningful way? As a generically you look at all the 5 pictures and tell which battery meets all the requirements. Especially as India needs all these 4 very important. The answer is NMC and LFP. So that is the reason that these 2 batteries are surviving in India. They are further, even not only in India, even other countries also. But why NCA is more used by Tesla? Because Tesla tried to optimize the battery and they have brought down the cost. However, even though the cost of the NCA batteries are higher, but they expect more specific energy and specific power. So compared to the other batteries, they have more specific energy and specific power, which they look at very important. And however, in India, Indian manufacturers, they look at the safety, lifespan, basically lifespan and the cost as the very important factors. And we decide that NMC and the LFP are the most suitable batteries for the EV applications. So let's discuss, right now, till now we have discussed about the cell, but now right now we are going to discuss about the battery pack design. What are all the considerations that we have to have when we are developing a battery pack? And these considerations will change from different applications. Either you are developing battery pack for a 2-wheeler or for an auto or for a car or for a bus. So depending upon the different vehicle application, this battery pack system design will change. So currently all the manufacturers are following this approach. We call it as cell to module to pack approach, right? Other than few companies, there are few companies which are not following the certain methodology. They have their own methodology. right? I hope you people can understand. So especially in the automobile, currently if you look at any most of the manufacturers, they follow this approach called cell to module to pack approach. So what happens is, this is, for example, in this case, this is a battery pack from one of the manufacturer. So in this case, you can see what does a battery pack contain. What they do generally, they make cells like, they collect the cells like this, either a pouch type cell. They decide which cell chemistry to go first. First, they will decide whether I have to go for lithium NMC or NCA or all these batteries chemistries we discussed. After deciding the chemistry, they will decide what type of construction we can go. Whether we should go for cylindrical or prismatic or pouch. So then, depending upon the available space, depending upon, say, available space in their particular car. Say, for example, when you compare Tesla Model S and Chevrolet Bolt, you don't have equal space in both the vehicles. So they both are extremely different vehicles, right? So they have the space variation is there always in both different vehicles, and depending upon their availability of space, they decide what type of chemistry or what type of construction of cell they can go. So when you look at a battery pack, basically, what does a battery pack contain? A battery pack has the main housing, the main structural housing, because it is actually a very safety critical component, and because of that, even during crash, any sort of crash or any impact, that impact should not reach the battery components, internal battery components. So because of that, we build a very strong battery housing. That is very important part of the battery pack. And depending upon the thermal management system design, sometimes we might have the cooling system integrated with the battery pack housing. Sometimes a company like Tesla, so they have a serpentine design. Means every cell to cell, they transfer an aluminum plate, and every cell to cell, it goes like a snake, right? Like the snake, they build this cooling lines. So different companies follow different strategies. Like I'll show some case studies in the coming slides. We will talk about Nissan Leaf and Audi e-tron. So I have taken some 2 case studies. So when you take the battery pack has these components. So one is the structural component, the battery housing, which is going to contain all the components of your battery pack. And inside the battery pack, if you go housing, you have the modules. So these are all called modules, battery modules. And inside the battery modules, you have the cells like this joined together. So for example, this battery module can contain some 10 to 15 cells. This will contain some 10 to 15 cells. Similarly, you will have some, say for example, if this contains 10 cells, one module has 10 cells, for example, then 1, 2, 3, 6 plus 6, 12. So 12 modules are there. So 12 into 10, 120 cells will be there. So every module will have some number of cells, and totally there will be so much of modules that will make the pack. We will understand it, how it has been built. In addition to that, what else is there? We also have the battery management system. As I told you, lithium-ion batteries, the battery management system is a very important part of it. So the battery management system, this is the battery management system component. I hope you people are able to visualize that. Let's understand the further the battery pack design. When you look at the battery pack, let's make a cost breakdown. When you look at a battery pack, basically what happens is nearly 60% of the total cost of the battery pack is related to the cell, and 16% of the cost of your battery pack goes to the BMS, and 3% goes for the logistics and the remaining wiring harnesses, and the remaining 18% goes for the labor, means the manufacturing side and the transportation side. So the manufacturing side labor or the machines we can consider. And when you talk about a whole, if say this is an EV battery, and if it is a hybrid electric vehicle battery, in that case what happens is the cell side requirement is 30% only, but in the hybrid vehicle side, the thermal management side, the restrictions higher. So 20% cost goes for the thermal management and 20% cost goes for the BMS. So when you people are working on a research project or anything related to battery pack, see, this is where your contribution comes. So if you do something, if you do some research work and that reduces the cost of the BMS, for example, then that is something which reduces this 20% to something else, right? So the cost breakdown, this is what the cost breakdown of a battery pack. And when you look at the cell, complete cell, in that cell, mainly the cathode material is playing the major role. That is just for your understanding. I just put you this in the slide. 42% of the total cell material is basically the cathode, consumes the cathode. and nearly 16% is with the anode, and 19% is the electrolyte is consuming the space, and remaining there are other materials in the cells. So when you how to decide the number of cells? That's a big question, right? So if I want to make a lithium-ion battery pack for a vehicle, say for a two-wheeler, how I will decide what is the number of cells I have to take for this battery pack? What is the parameter to consider? So the first very important parameter is what is your motor design requirement. So if you remember, there were few parameters that we saw on the motor inverter side. Actually, what is the thing needed from the battery? Do you remember the controller part? Do you remember the controller picture as shown yesterday? There, the battery is providing something to the motors, the inverter. What was that? What are the three parameters that the motor controller needs? We saw three parameters that the battery has to provide for a motor inverter: battery current, battery power. So battery current and the battery power. So battery power, we will take the battery power. So power is nothing but your voltage into current. So end of the day, I need certain voltage and certain current. So in the battery pack, what happens is, depending upon what is your motor's design requirement, that means what is your motor's continuous current, what is your motor's peak current. Based on these two parameters, we decide what is the voltage and what is the current required, especially the voltage. So what is the requirement or required voltage of your motor, right? Depending upon the voltage requirement, say for example, I want to have 100 voltage. So now I have to decide, okay, I need 100 voltage. And you know, all the chemistries don't give the same voltage, the nominal voltage, right? It will change from one cell to another cell. I told you that nickel, say for example, nickel manganese oxide, nickel manganese cobalt oxide. So we know that, we saw that in the earlier slide that yes, all the batteries, say NMC, lithium nickel manganese oxide battery, will have 3.6 voltage per cell. And if it is ferrophosphate, it will have 3.2 nominal voltage per cell. And if it is lithium titanate, it will have only 2.2 nominal voltage per cell. So what will happen? Say if I have, can you people calculate it? Let us see. Let me tell you. Let's do this calculation from our side. Say if I am making a battery pack, participants kindly follow up with me. I am making a battery pack. I expect the voltage I need for the battery pack. That means the voltage that is needed to run my motor is 360 voltage. So I need that 360 voltage from my battery also. So if I select nickel manganese cobalt oxide as the battery, how many cells will I need to make 360 voltage? Can you people calculate? You know voltage, how voltage is brought? It is brought when the series cells are connected in series. So when the nominal voltage per cell is lesser, then you need to put more and more cells in the system. So the size of your battery pack will keep on increasing. So the nominal voltage per cell is one of the very important parameter when we are selecting the deciding the voltage of the cell, right? And one more thing is, you understand that when you are deciding the module. So I told that in the previous picture. Let me come to the picture. Wait. Yes. So when you look at this picture, you have one module. I told you one module will have some 10 to 15 cells, right? And that completely depends upon one parameter called cell supervisory circuit. See, I told there is a battery management system for the whole battery pack, but irrespective of the battery management system, there is also something called cell supervisory circuit. That means for every model inside the battery module, every module there will be a controller. We will talk about the controller in the next part of the session, but understand that there is a special controller, dedicated controller for every module. So that controller can only handle somewhere close to 10 to 12 cells per module, right? There is a limitation for that. So you cannot decide so much of cells inside one module, right? So every module can only handle particular number of cells only. So these parameters you have to decide whether you have to go for an even number of cells. And second thing is, what is the cell supervisory circuit that you are making? That cell supervisory circuit's limitations are there. So if it can only handle 12 cells in one module, then you have to put only 12 cells in a module. Now tell me, how many modules will I need in this case? Say, in this case, I am telling that one module can handle up to 14 cells. So in this case, there are totally 100 cells in series actually. So one module can handle 14 cells. So how many modules will be there? Can you people calculate? So somewhere approximately close to 8. So what happens? So look at this picture that we understand that, depending upon the cell voltage, nominal voltage, the number of modules and the number of cells in series will change, right? And the same principle is applicable for the current also. So when we take a battery pack, there is one more parameter called AH, the capacity, and the capacity is completely dependent on what is the continuous current requirement for your motor, what is your peak current required by your motor. Based on this parameter, we decide what is the AH value. Let's look at this picture. If I say, like for example, when I make a lithium ion, this is a lithium manganese cobalt oxide, same ferrophosphate and lithium titanate. And when I have 10 capacity per cell, 10 AH per cell, if it is common for all, well and good. If it is common for all, well and good. But now can you calculate, guys? Can you people calculate if I want 120 AH? Can you people help me to fill this table? If I want to make a battery pack with capacity of 120 AH and my per cell capacity is only 10 AH for NMC, 20 AH for ferrophosphate and 5 AH for titanate. Can you tell me how many cells will I need to connect in parallel, right? So what happens is, in this case, basically the module control is basically on the voltage capacity, also the current capacity, right? What happens is, based on these two parameters, as I mentioned, based on the two parameters, you decide the continuous current. So when you talk about, that is why I told, whenever you select a battery, we cannot blindly select a battery. We have to say we are putting a motor for your vehicle. We have to go to the motor manufacturer. We have to ask him what is the total continuous current of your motor, what is the peak current of your motor. Based on that only you should decide the battery pack. In sometimes I am seeing motor department is working somewhere in that side, battery department is somewhere in that side. They are not having any communication between them. Then how come a battery pack will meet the motor requirement, right? Obviously they should have a communication between them, and it is like a team effort. Both the data is very, very important when they are developing this thing. And let's talk about a very important parameter in the battery pack, C rate. Say guys, understand that when you talk about electric vehicle, we decide the battery pack design based on two parameters. Whether you need a very high performance battery pack, or whether you need to, that means whether you need a high performance vehicle or you need a very high efficiency, like very high range vehicle. What is your requirement? Whether if the range is the requirement, is the primary concern, then the battery pack that you make should be called as energy battery pack, energy type. If performance is the demand, is the main criteria, then you have to call it as a power type battery pack. Can you understand the difference? Look at these two graphs, guys. Look at these two graphs. This is an energy type battery pack, and you can understand that these energy type battery packs, they can withstand up to 3500 mAh capacity. That means it can extend its lifetime for a very long time. It will slowly discharge. And when you talk about the power cell, power type of cell, where you need very high performance, they will quickly discharge. Say from 4 volt to 3.5 volt and 3.5 to 3 volt, very quickly they'll come. Within 2000 mAh, they'll come. This is power type batteries, whereas energy type batteries, where you will get more range, they will discharge very slowly. The time taken from 4 volt to 3.5 volt will differ for this cell to this cell. And what happens is, C rating means how much current that battery can supply. For example, I will show you a picture in the coming slide, and that will be a very clear thing. Let me take the picture here, and then it will be better. Let us look at this picture, guys. This is an example of a lithium-ion battery. This is manufactured by a company called Hexacom. Okay, manufactures lithium-ion battery. And look at this parameter. So very important thing, the parameter, the lithium-ion battery parameter. Look at these values. Look at these values which I'm showing here. This is the specification sheet of the battery pack, and in the specification sheet they mention what is the nominal voltage of this battery pack. 51.2 voltage. It is a whole battery pack's voltage, guys. Okay, it is not the cell voltage. Okay, it's the nominal voltage of the battery pack. And what is the charge current? 37.5 ampere. What is the discharge current? 35 ampere. Nominal discharge current. And what is the peak discharge current? How much? It is 95 ampere and only for 10 seconds. That's what I told. Peak means only for a few seconds it can withstand that current rating. So look at the nominal current. The nominal current rating is actually 35 amps. Say for example, the nominal current rating is 35 amps. Can you tell me how much times is 95 amps from 35 amps? Can you calculate it how much times it is? 2.714 times. It's almost 3 times, right? It's almost 3 times the nominal current. That means what? It is called as 3C. It is called as 3C. So here in this battery, the nominal current is 35 ampere. That is called the 1C rating of this battery. And the peak current is actually 3 times the nominal current. We call it as 3C. So peak manufacturer, they will say this battery is nominal discharge 1C and peak discharge 3C. And what else is deciding this 1C? 1C is not only from this parameter. Let me take a picture for you. An example lithium ion battery. Let me take it for example, guys. This is an example, a company called Electrovaya. Look at this. This is a cell, a single pouch type cell, a single pouch type cell, right? Look at this cell. The cell is having a nominal voltage of 3.65 and it is having a peak voltage of 4.2 and it is having a minimum voltage of 3.0, right? What happens is, what is the capacity of this battery? 44 ampere hour. They mention nominal capacity is 44 ampere hour. 44 ampere is the nominal current. So when I am saying charging continuous 2C, 2C means what? How much current? 2 into 44 ampere, 88 ampere. And when I am saying pulse, 4C means what? 176, I believe, right? 176 ampere on the pulse charging. And similarly, when I am saying discharge current, it is 3C rating. So 3C rating means 3 into 44. It will be somewhere close to, I believe, 132. Is it right? 132 ampere is the 3C discharging. So up to 132 ampere current you can discharge from this cell, capability of this cell. And pulse discharge, 10C, that is for only few seconds. 10C means how much? 440 ampere. Now can you imagine when an electric car, why an electric car uses the pouch type cell? Some of the electric cars, they use pouch type cell. They are able to deliver a very huge amount of pulse current. And you know when this pulse current will happen? Pulse discharge current, when this will be needed in an electric vehicle. So depending upon a sudden acceleration, intermittent acceleration, or if you put very heavy load on your vehicle, in order to move for the first initially few meters, it will consume huge amount of current, right? So the pulse current will, most of the time, it will last for only for 10 seconds maximum, 5 seconds, 10 seconds, 2 seconds. So when we purchase a battery pack from a manufacturer, it is our responsibility. Sometimes the manufacturer will not tell you. Sometimes the battery manufacturer will not tell you what is the current pulse rating and all. It is our responsibility when we are developing an electric vehicle. It is our responsibility to make sure that you know that pulse rating. And what happens is, if you don't know the pulse rating, and when you select a motor and controller, you will wrongly select the motor controller, because according to the pulse capacity, the pulse current capacity of the battery only, we should select and look at the life cycle they are given, 6,000 cycles. 6,000 cycles. This pouch cell, it is having 6,000 cycles of capacity. I think it's a Canadian company, I believe. I remember it was a Canadian manufacturer actually. This is an example of a cell battery generally, right? I'll talk about the BMS and the other parts in the next upcoming sessions. So what happens is, when you're selecting the battery pack, that is very, very important. The nominal capacity is very, very important, guys. I'll come to this slide once again at the later stage. And what else is very important? When you talk about the charging rate, that C rating, 1C, 2C, 3C, this C rating will affect your life cycle. Higher and higher, the more and more C rating you go, the life cycle of your battery will come down. And this will also have the effect with the temperature also. When you are making a thermal management system for a battery pack, it talks about the duty cycle. We have to consider what is the duty cycle of your vehicle. Say if it is a very heavy truck, you imagine very heavy truck which is going to carry huge amount of tons of load, then in that case, yes, the demand is every time the vehicle stops and starts, there will be a huge amount of current consumption. That is the type of duty cycle. And if I say a two-wheeler, if I say a two-wheeler, only for already the total capacity required for two-wheeler is very less. And the total lifetime, how much time, whether the out of 24 hours, how much time the product is going to run. Say when you are developing the battery pack thermal design, you have to understand the parameter that what is the duty cycle. Out of 24 hours of time, how much duration the battery pack is going to run. Say for example, if it is an industrial application, 24/7 it will be running. 24/7 it will be running. And if it is a vehicle application, it is not 24 hours. Depending upon the vehicle category, it may work for 2 hours. Say for example, if it's a two-wheeler, I'll be using for like office purpose. Morning 8 o'clock, I'll go from my home to office. 1 hour it will be running, and evening I'll be coming back. This is the duty cycle. So depending upon the vehicle category, if it is an auto, electric auto, full day it will be running. If it is a electric car, which I'm using for Ola, Uber, 24/7 it will be running, right? Shift basis it will be working. So depending upon the duty cycle of the battery pack, that particular application, that is also one factor that you have to consider. So when you talk about the thermal management system design, operating environment is also very, very important. So we know that the operating environment is different in Chennai, different in Karnataka, Bangalore, and different in Canada, Europe. It is not same climatic condition. The same battery pack. So today, if you see the Nissan Leaf, Nissan is testing their Nissan Leaf vehicle in Chennai, and they are seeing that their battery is not performing good as it is performing in Japan and other countries, because the operating environment is completely different. So when we develop the thermal management system, these factors are very, very important. Even the cell chemistry and the construction type, also very important. Right. So when we talk about the thermal management system, what we understand is basically the purpose of using thermal management system is not to cool the battery or heat the battery. Basically, it is to maintain the battery in a temperature range, in a proper optimal temperature range. So it avoids, the thermal management system makes sure that the battery will not go to the extreme hot climate or the extreme cold climate. That's what the main purpose of using thermal management system. And why we need a thermal management system? Because when the batteries go extreme hot or extreme cold, they will age faster. Their lifetime will come down. And to increase the battery's calendar life, we need to have a proper thermal management system. So this is an example of a thermal control diagram. So we have a battery management, we have a battery system. Depending upon the temperature of your battery pack, whether the battery pack is getting too hot or too cold, we know generally the HVAC. Everyone know what about the heating, ventilation, air conditioning system. It is the same thing here also in the battery packs also. So this is a typical thermal control diagram of an electric vehicle battery pack. But the thing is, in this case, I have shown you only the battery pack. But when you talk about electric vehicle, it is not the battery pack only cooled, it is also the other components, even your traction inverter, even your motor. So yesterday you would have seen the picture of Audi e-tron. There is a coolant circulation on the motor. That is nothing but the same coolant which is going from here. So what they do is, currently the EV manufacturers, they use the same coolant throughout all the motor, controller, inverter, onboard charger, all the components are cooled by the same component. Sometimes, depending upon the requirement, they will have a dedicated thermal management system for battery packs also, depending upon if their requirement. Right? So when you look at a battery pack, see for example, there is a chiller, there is a radiator. So depending upon the temperature sensed by the battery, by the module, they will decide whether I have to open the valve of the radiator or the valve towards the chiller. If the battery is very hot, if the battery becomes very hot, then they will open the valve towards the chiller. So the coolant will go to the chiller, it will go, temperature will come down, and it will come back to the battery pack. Right? So when we talk about the HVAC part, yes sir, so this is general, it's a conventional HVAC only. But the thing is, depending upon, say when I don't need a cooling or when I don't need a heating, immediately what will happen? It will go to a bypass. It will not go to either a radiator, it will not go to either a chiller, it will bypass directly to the battery pack. Like our IC engine cooling only. So depending upon the battery temperature. But let me see different thermal management systems. See, the thermal management system today, it is being done with two types. We call it as active thermal management, one is passive thermal management. Active thermal management means continuously, whenever the vehicle is running, your cooling medium will be actively working on. Say the active thermal management will be like air, using air it can be, or using a liquid. Like we will mix water and glycol and we will circulate it inside the battery pack. It is called liquid type. So currently if you take Tesla, so Tesla is using liquid type. thermal management. And if you take Chevrolet Bolt, Chevrolet is using a liquid type thermal management only. And air also is one of the mediums. The disadvantage of air, what is the disadvantage that air gives is relatively effective in responding to the rapid changes in temperature. Compared to the liquid medium, very quickly the air will travel inside. And compared to the liquid cooled system, it will be lightweight, right? It does not need a specific channel to go through, and it will not consume heavy weight channels. So the total thermal management system weight will be reduced when you go for air. But when you compare to liquid medium, effective medium is the liquid only. Effectively, like compared to the air medium, like transferring the heat from away the cells to cell, effectively it will happen in the liquid medium. And what else is the thing is, it can also, with the heating element in the system, you can also heat the system. When you, depending upon heating or cooling, you can use that flexibility is there. And you can see that cold climate, when extremely cold climate, you can add glycol into the system, and that glycol will try to, we all know that glycol is an anti-freezing agent, right? So when your electric vehicle goes into an extremely cold climate, then this makes sure that the battery still works in a nominal work area. But if you ask me currently, yes, battery packs are not 100% properly working in extremely cold climates, especially people who are in USA and Canada. Especially people who are in Canada experience this, and I have seen so many diagnostic problems that comes in the cold climates. But however, in our India's case, this problem is not there. India's case, we don't have such very extreme climate conditions and all. It is very, very rare, right? So in that case, India, we don't have, it's a good temperature, especially the areas like Chennai and these areas, they are having good temperature range, 20 degree, 30 degree, 40 degree. These are all good temperature for a battery pack basically. When you cross this 40 degrees Celsius, then only the problems comes into picture. And some companies, they don't use cooling system also. Do you know? There are some companies which don't use cooling system for their battery pack in their car. For example, Nissan Leaf. Nissan Leaf, initially they did not use any cooling system in their battery pack. They used some systems called passive thermal management. Without using a liquid cooled system or without using a air cooled system, there are other ways of cooling a battery pack. We call it as passive thermal management. What we do here in this passive thermal management, I think that picture that is missing from here, it should be kept here. Sorry. So what we keep, passive thermal management, what they do, they will put some coatings on the battery pack. Below the battery pack, below the module, every module, they will apply some special coatings. These coatings will have a tendency to absorb the heat from the battery pack. At the same time, especially we also use, some companies, they are also looking for phase change materials, PCMs. So these phase change materials, instead of using a air cooled and water cooled system, people are now looking on the phase change material as an alternative, where these phase change materials will, depending upon the temperature of that particular temperature, they will change their phase from one phase to another phase. So instead of coming in a pure solid phase, they'll go for semi-solid phase, and the different phases is also possible. And once the temperature comes down, immediately they'll return to the old phase. So we call it as phase change materials. So currently, electric vehicles, there's a huge research work going on the phase change materials also, rather than using a coolant like this. So other than active, that is it is called passive thermal management. And what is the advantage of this phase change materials and the coatings what we give? These materials bring down the cost drastically. These materials bring down the cost drastically. Because of that, you will have the thermal management system cost will come down. And not only the phase change materials and coatings, even the housing, even depending upon what material you use for the designing of the housing, that is very, very important. So some people use steel. Some people use aluminum, right? So depending upon what type of material we use for the housing, that will also contribute for the thermal management system, right? And when you are selecting the coating is not only for thermal management, even for structural stiffness. If you remember this picture, guys, let me go to the picture and do that. When you look at this picture, we understand that the battery modules are fixed with the battery housing. What they do is they generally put some battery adhesives below this battery pack. they put some adhesives. You can see that they'll keep coating on some special coatings below the module. Those coatings are doing two jobs. One is they work as a structural adhesive. So whenever there is a vibration in your battery pack, whenever there is a vibration in your electric car, the modules will stay rigid. The modules will not move from that place. So the coatings will work as a structural adhesive. At the same time, they also transfer the heat from the module into the battery housing. They will transfer the heat generated by the module into the battery housing. We call it as thermal coating as well. So the coatings what I mentioned here, they do two jobs. One is structural adhesive. They work as a structural adhesive, and they also work as a thermal management system also. So when you are selecting a coating system for a battery pack, you have to ask yourself these questions. Right? I am not going deeper in that perspective right now. We don't have much time for that. But understand, look at this, read these parameters and read these characteristics. What are all the things I have to consider when I am making a battery pack housing? These are the questions that you should ask as a design engineer. What is the application? Whether it is a two-wheeler, whether it is a three-wheeler. For a two-wheeler, I should not put a very highly sophisticated thermal management system on all. It is not necessary, right? A two-wheeler is going to be just 2-3 kilowatt, 4 kilowatt battery pack, for which you don't need a special dedicated thermal management system on all. Not required. A thermal management system will be required only after certain power level. So depending upon the application, it will change where your battery pack will be mounted. Whether you are going to mount the battery pack like this in the middle of the car, whether you are going to mount the battery pack in the front of the car, whether you are going to mount it in the rear of the car or below the bottom of the car, ground level. So all these factors are there when we are selecting the battery pack. All these factors are decided when you are developing the package design. Where it is mounted, whether it is mounted on the hood, on the passenger compartment, what type of sealing is required. We'll talk about the sealing in the next slide. What is the sealing that you need for the battery pack? Whether you need a waterproof sealing, whether you need a dust-proof sealing, that is also to be considered. And is it a structural component? What do you mean by structural component? Guys, anyone, can you tell me? What is meant by structural component? If the battery pack, is it a structural component means what? What about crash safety? Crash safety. So if there is a crash happening for the electric car, how the structural members are going to give strength? So whether my battery housing is itself part of the frame, that is what the question we have to ask. Yes, we can do that also. We can make your battery pack housing as part of the structural member, or whether it is carrying the load of other components, right? That is also a question that we have to decide on your battery pack. And what type of shock and vibration conditions that your vehicle is going to experience. If you are developing a vehicle for India, what do you think, whether this question is important or not? Especially India's road conditions. So you will understand that Indians are considering that when you talk about the testing that is happening in that tomorrow. We'll talk about the testing for the battery pack tomorrow. You will understand, yes, they have considered it for India. Then not only for India, you can say worst case condition, like for example, mining. If I use a vehicle for mining condition, it is the worst case scenario, extreme temperature, extreme road conditions, right? So worst case conditions we have to see when you are developing the mechanical packaging. And moreover, considering all these things, other important thing is electromagnetic interference. Whether your battery is having any specific electromagnetic interference compatibility requirements from the industry. Say if it is a two-wheeler, it is not much challenging. But if I am making an electric car, the EMI EMC problems should be addressed properly. So depending upon the application, the EMI EMC problems will be very, very higher. So you have to develop a battery pack according to the application. And distance to other heat generating components, that is also very important, right? So when we are talking about power density, so yesterday we told that the inverter is being very closely kept to the motor. Correct? The battery pack has to be bring as much as closer to the motor, because I can reduce the cable size, cable length. Correct? But when I'm bringing it very, very closer, what will happen? Whether there is a generation of heat from the motor that could affect my battery? That's the question, right? Whether the heat generation from my inverter could affect my battery pack. So these are also the things that we have to decide, we have to consider when we develop a battery pack system design. And the final thing is serviceability. Serviceability. We easily make we easily design battery packs, but we should think on the service perspective also. In future, if there is any problem, whether the customer has to replace the whole battery pack, or he can replace only the one module which contains 10 cells, or is it possible for him to replace every cell he can replace. That is also important, right? So if I am telling you, sir, if I am telling you, sir, that you can purchase the car from my vehicle, from my company, and I am telling you after 2 years this battery will go, and you have to replace the whole battery pack for 5-10 lakhs. Will you purchase my car? Serviceability is very, very important, and that should be considered when we are designing in the design phase also. So we should think that in future, if the customer replaces, if there is a problem in the battery pack, whether the customer needs to replace the whole battery pack, or so what is the minimum replaceable unit? We call it as minimum replaceable unit. So today, if I go for a petrol diesel car, I can replace some of the small components, right? Maruti Suzuki, the success of Maruti Suzuki is the serviceability. You can spend 1,000 rupees, 500,000 rupees, 2,000 rupees and replace the part. The failure of some of the companies, especially you can say some OEMs, I don't want to mention their name, they failed in India because of their serviceability, because their spare parts were very, very costlier. And you have to replace the whole unit instead of one simple component. You would have, the problem might be in only one small component, but they will tell, so no sir, you have to replace the whole unit. Maybe you customers, audience can give me some companies if you have experienced it. Okay, Mr. Jahir has experienced it with Pulsar, he is telling. Okay, it's up to you, it's up to your experience. Yes. So serviceability is very, very important, and when we are talking about electric vehicle, serviceability is very, very important. That is why Tata Motors is giving 10 years warranty for their battery pack. 10 years, you don't need to think about the battery pack. You don't need to worry about the battery pack. And when you talk about the material enclosure, that means the enclosure design. I told the housing, right? The material housing. What is the material I have to select? It is a very important thing. Whether I have to select steel or aluminum or plastic, what type of material I should go for the battery pack enclosure. So that's a very big question that we have to ask. It is not very easily decided. So when I say, if you ask a passenger car, now there is a question for all the participants. All the participants, kindly listen to my question. There is an electric car accident. Okay. And there is an electric car. 2 electric cars are having an accident. One electric car is having a battery pack made up of steel. And one electric car is having a battery pack made up of aluminum. Now tell me which car the passengers are quite safer comparably. Could you participants tell me? See, the problem is here, when I am talking about a crash, very specifically I am telling crash. So when I am telling a crash, a very high speed crash of an electric vehicle, what happens is, actually electric vehicles will not catch fire up to say a speed of 120-130 km per hour. I can tell you that up to 120-130 km per hour, if you have a crash, electric vehicles will not catch fire actually. That is how they are being tested. You will understand that by tomorrow. But if there is a person who does a crash, he travels more than 150 km per hour and he did a crash. And now imagine that the electric vehicle catches fire. Now tell me which, as you told, the answers are more towards, both the answers are there, steel and aluminum is there. But if you ask me steel, so if you ask which material is having highest melting point? What is the melting point of steel? How much degree Celsius, guys? What is the melting point of steel? It is somewhere more than 1400 to 1500 degrees Celsius. Right? Whereas for aluminum, it is 600 degrees Celsius. 600 plus degrees Celsius. So what happens when there is a fire in your battery? Your aluminum batteries will quickly catch the fire. They will immediately melt. And aluminum steel batteries will take time to catch fire. Because of that, the customers will get time to escape from the battery, from the vehicle. If in case I don't know if you go and if you drive the vehicle at 175 kilometer, 200 kilometer and make a crash, no one can save you. Yes, no one can save you. Even God cannot save you if you drive such a high speed, right? Even manufacturers do say this same word. There was a fire accident happened in Toyota, I think, within a Toyota car, and that catched fire in China. And reporters asking, sir, why your vehicle got catched fire? He told, sir, that particular driver who was driving the vehicle, he was driving the vehicle at extreme speed. In this speed, even God drives the vehicle, it will catch fire. That's what the people said into the press. Right? So there's a limit for any vehicle. There is a limit up to which it can withstand the force, and that is clearly given in the testing scenario. They will give it. So when you talk about enclosure design, depending upon either you have a depending upon a two-wheeler, it is a two-wheeler or three-wheeler. If it is a electric car or a bus or a truck, the enclosure design can change. The material selection can change. Even there are some applications where polymer, plastic has been used, fiber reinforced FRPs have been used instead of metals, right? So it depends upon the application, depending upon the stiffness, what you expect from the material, right? And the final thing when you are talking about the material housing is the ingress protection, IP rating. What is the IP rating? What is meant by IP rating? Ingress protection. So the IP rating means, say, when you remember the battery pack. When you remember the battery pack, look at this battery pack provided by the manufacturer. He has specified some IP rating. What is the IP rating, guys? What he specified here? Can you people identify that for me? IP65. That is what mentioned by Exicom. What is meant by IP65? So the first digit IP means ingress protection, and what is the 6 means? 6 is in the dust proof. So IP65 means 6 means it is completely dust proof. Dust will not enter into the battery pack. And 5 means waterproof. What is the 5 means? Water up to 30 kilopascal pressure. That means we wash the electric vehicles, right? We can wash an electric vehicle. We can water wash an electric vehicle up to 30 kilopascal pressure. It can withstand the battery. The water will not enter into the battery pack. That is what we call it as IP65. And when you look at the battery pack made by Audi e-tron, it is made up of IP6K 9K. Audi e-tron's battery pack, I will show the case study in the coming slide. It is made up of IP6K 9K. That means up to 1000 kilopascal of pressure it can withstand from the water, and up to 9, that means up to even the high temperature water also it can withstand. That is why they call it as IP6K 9K. It is the highest rating possible for a battery pack. That is what achieved by Audi e-tron. Whereas most of the battery packs that we use in our electric cars and electric two-wheelers are all basically IP65, 66, 67. 67 is quite costlier because, and that is what the rating used by Ather scooter. Because of that reason only their cost is higher. Why? Because why they need IP67? You know India. You know Indian conditions. You know flood conditions. Right? Every year we face floods. So without IP rating of IP67, how I will say electric vehicles are safer? Right? So definitely yes, IP67 is a very important rating that will be needed for a case of India. At least IP65. Right? And most of the manufacturers today, you will see that minimum IP65 is there, definitely. BMS, one of the major part of the battery management system of the lithium battery packs is the battery management system. So what does a battery management system do generally? What is the function of a BMS? What does it do? So when I classify its overall function in an electric vehicle, the battery management system plays a very important role in the battery packs. First one is one of the role that it plays is the energy and power prediction. Just look at this picture. So it is a battery energy and the battery's power prediction is being done by the BMS. What is meant by prediction? like it measures some parameters, it measures some parameters, and it calculates some parameters, and it monitors some parameters, because it has to keep all the things in control in the battery pack. So battery energy monitoring, you can say, energy prediction and power prediction. So whether, say, if this battery management system is the one that tells you how much kilometer this vehicle is going to go, how much kilometer the vehicle can be run. Or when I do charging, this is the BMS is the one which tells you how much time will it take the charging to complete. So complete energy and the prediction is being taken care of by the battery management system. We'll talk about these parameters. And other than that, monitoring and diagnosis, that is very, very important. What is that BMS doing is, it measures the voltage. Kindly note down, guys, kindly note down, this is very, very important. So when a BMS measures these parameters, without these parameters, a BMS function cannot be complete. It measures the voltage of the battery pack. It measures not the battery pack alone, it measures the voltage, current, temperature of the cell, as well as the module, as well as the pack. It measures the voltage of the cell, voltage of the pack, and it also detects if there is any leakage current flowing in the battery pack. It prevents any accident or anything danger happening to the battery pack. So it keeps on watching the battery pack, every inch of the battery pack, if there is any leakage current flowing there. It also detects if there is any isolation resistance. So the proper isolation resistance is provided between the battery pack and the other component. So yesterday you saw that, I think day before yesterday, right? We saw that some fuse and MSD, manual service disconnect. You remember, right? You remember those things? Yes. So all those things are being controlled by the battery management system only. All the switches, everything is being controlled by the BMS only. So it diagnoses completely that what is the isolation resistance, actual isolation resistance required, and whether that resistance is there in the whole vehicle. So because if there is a short circuit, it is detected. So everything will be detected and diagnosed by the battery BMS. And more than that, I told you, right, the controller, the contactor actuation, that is coming under the actuation part of the BMS. And what else it is also doing? It is also doing the lifetime enhancement. When the driver, say when we are purchasing the electric two-wheeler, electric scooter, electric car, it is same for all. But the style Prashant is driving is different. The style some other person he is driving is different, right? So that the usage pattern is completely different, and because of that usage pattern, there will be a degradation on your vehicle more than expectation. There will be more degradation maybe. So your battery has an intelligence that it will try to enhance the battery's lifetime, even though the driver is not using it in the right way. The battery itself has an intelligence that it tries to enhance its lifetime by properly maintaining the temperature, by properly balancing the cells. As Sir was mentioning, I think Sir was asking the balancing. He called as alignment actually, but in our terms we call it as balancing, equalization. So that is also done by the BMS, and you have the communication. At the end of the day, finally, if there is any problem in your battery pack, if there is any safety related issue, immediately that information should be given to the customer or the manufacturer or the driver, whoever it may be in the vehicle. It has to be given to the customer. So that communication is also part of the battery management system. And when we look at the lithium batteries thermal side, when the lithium battery performs at different temperature, you can understand from this picture that depending upon the temperature at which it is working, there are different problems that can happen. So when the temperature, for example, when that battery's temperature crosses more than 60-80 degrees Celsius, that comes under the over temperature zone. Immediately what will happen? Because of this over temperature zone, there will be immediately a layer, we call it as SEA layer actually. This particular SEA layer is basically in the battery cells, inside the cells actually, right? When you have emergency, like when the temperature of your battery is going in such a heavy higher rate, right? So we call that as a depreciation. It will actually affect the SEA layer. So basically what happens is, so this layer is actually in the in the silk construction. We call it as solid electrolyte interface layer, SEI layer, that is in between the cathode and the anode. So this layer prevents the short circuit and many forms of damage of the battery. So this, sometimes when your temperature crosses a certain limit, this SEI layer will break down. This SEI layer will break down. And when this SEI layer, SEI layer break down, the solid electrolyte interface layer break down, then immediately what will happen? This will lead to thermal runaway of your battery. So immediately your BMS will be informed. Your BMS will know this because it is keep on monitoring the voltage and all the parameters. So it immediately shutdowns the system. It completely stops sending the current flow to the battery. That means to your motor inverter. And when your battery pack temperature goes above 120 degrees Celsius, what will happen? What will happen? Immediately, if the temperature goes beyond that ranges, says the separator will melt. There is a separator between the cathode and anode. That separator layer will melt, and this will lead to short circuiting. So before that, what will happen? The BMS will be disconnected. That means the BMS will disconnect the battery from the whole system. But in some cases where there was a very huge accident and immediately the temperature went to a range of 190 degrees Celsius, the cell temperature, that we call it as thermal runaway. If the temperature went to this region, if the temperature reaches this region, nothing can be done on this side. The only thing is cell destruction will happen there. So the BMS plays a very important role, that the temperature is maintained. So the BMS makes sure that the temperature is in the safe operating region where these kind of problems will not come. Let me take this picture. This picture is enough to explain the complete BMS to you all. Just look at this block diagram very clearly. Imagine this is your whole battery pack. And you imagine that, you remember there were so many battery modules were there, right? There were so many battery modules. Say module 1, module 2, module 3, module 4, like that. There were so many modules. So when you look at a battery pack, inside the battery pack you have the module. So what we do is, for every module there will be a cell supervisory circuit. I have told it earlier, but I'm showing it here. You can see there is a cell supervisory circuit near to every module. So in a whole battery pack, if there are 20 modules are there, 20 cell supervisory circuits will be there. And all the cell supervisory circuits, they are called as slave circuits. What they are called as? Slave circuits. And all the slave circuits, they collect some information and they provide the information, they report to some master. They are called master unit. We call it as the battery monitoring unit. It is the battery monitoring unit. So what happens here? Here every module will have a cell supervisory circuit. So what happens? We split the functions. Some functions are performed by cell supervisory circuit. Some functions are performed by battery monitoring unit. Both are different. But end of the day, who is the deciding authority? If you ask, the final deciding authority is the battery monitoring unit only. Based on his instructions only, based on the instruction of BMU only, the cell supervisory circuit will be able to work. So what the cell supervisory circuits are doing, basically, they collect the information. Every module, I told, every module will have some 10 to 15 cells joined together. So what will happen? These cell supervisory circuits, they are basically monitoring and measurement units. They measure the voltage of the cell, they measure the temperature of the cell, and they measure all the parameters and give that information through CAN communication into the BMU. You know CAN communication, controller area network. This is one of the safest communication protocol used in automotive domain. And you know there are so many communication protocol, RS485. There are so many other protocols are there, right? But specifically automotive domain, wherever, especially even inside automotive, there are so many other protocols are used. CAN protocol, LIN protocol, FlexRay. There are so many protocols are there. But when you talk about safety, whenever you have, say, can you tell in a car what are all some safety components? Very important safety components in a car. Say, for example, can you tell airbag? Can I tell seat belt tensioner? So these components are very, very important because it prevents the life of the passenger. So these are coming under the special safety critical categories. So those components will be generally they use CAN communication protocol. So what happens is the cell supervisory circuit measures the voltage, temperature and keep on giving this information to the BMU. And the moment the BMU comes to know that there is some problem in terms of temperature limit, they will compare the temperature with the threshold temperature. Say for example, cell voltage. Let me take the cell voltage example. I told you that the cell voltage will range from, say, let me take an example of lithium NMC category cell. A lithium NMC cell, the nominal voltage is 3.75. When I fully charge the cell, it will go to 4.2. And when I fully discharge the cell, it will go to 3.0. So the operating range of the cell is 3.0 to 4.2. If the voltage of the cell grows more than 4.2, it is dangerous. If the voltage of the cell goes below 3.0, the cell will get damaged permanently. It will not come back to the life. So the cell supervisory circuit makes sure that the voltage will not cross 4.2. At the same time, it will not cross the lower threshold 3.0 also. But whenever during some temperature rise has happened, suddenly the temperature gone more than, say, the voltage has crossed 4.2, immediately what will happen? That information will be provided to the BMU. And your cell supervisory circuit also has a circuit called balancing circuit. Right? So this balancing circuit, what it will do, say for example, if in a module there are 10 cells are there. 10 cells are there. Out of 10 cells, one is 4.2, one is 4.1, one is 4.1. All the cells are 4.1. One cell is 4.3. What will happen now? I have to bring down that voltage of that particular one cell. Otherwise, what will happen? That cell will go to thermal runaway. It will damage the cells. So what we have to do? The cell balancing circuit will get activated. Let's see how it is done. I'll come back to this picture once again. These are all the things. Don't think I am skipping the slide. It is actually the thing which I explained you in the picture, in my words. It is just as the words it is shown, I'll show that. So when you talk about cell balancing, there are two types of cell balancing are there. One we call it as active balancing and one we call it as passive balancing. So what happens? Let us see the active balancing first. See, for example, this is a module. In this module, I have some 1, 2, 3, 4 cells are there. Consider. There are 4 cells are there in this module. So what is meant by active balancing? In this active balancing, what will happen is, say for example, if this cell is crossed 4.2, it has went to 4.3 volt. And this cell, it is somewhere in the range of 3.9 volt. Now what will happen? Active balancing means what? It takes the cells, it discharges the cell which is having higher voltage, and without wasting the energy, it transfers that energy into another cell. That's it. So using this is an example of active balancing. We call it as capacitive based active balancing. What we do is we take the excess energy from the cell and store it in the capacitor using the switch, and then we transfer the energy to the another cell whenever required. So this can be used using this can be performed. These switches are controlled by what? These switches are controlled by the battery management system. We have the MOSFETs basically sitting here. These MOSFETs are controlled by the battery management system only. So when it detects that this cell is crossing the voltage threshold, immediately that signal will come to the S1 switch to turn on. Immediately the S1 switch will open, close, and immediately it will get charged the capacitor, and then the switch 2, S2 will get charged, closed, and then the charge will transfer from the capacitor to the another cell, which is having lower voltage. So like this, the battery management system tries to balance the voltage from one cell to another cell using a capacitive approach, using an inductive approach, and you can see in this cell, using a transformer approach also is possible. Depending upon what type of BMS, what type of active balancing you can go for, depending upon the price and many factors are there. This is like it's a beginning level training. I don't want to go deeper into that, but understand that we can do the active balancing at capacitive, inductive level, and transformers, using the transformers as well. Right? So one cell to another cell. So here what happens? We are not wasting the energy. So excess energy is transferred to another cell. That is why it is called as active balancing. But there is one more type of balancing. We call it as passive balancing. Where in this case, if this is one cell, and this is one more cell of the module, if this cell is having higher voltage, it has crossed the threshold voltage, immediately the switch will be activated by the BMS. It will connect it to a resistor, and the energy from this cell will be dissipated. The voltage from, if it has crossed 4.3, then it will be brought to 4.2 or below 4.2 by dissipating the energy through the resistor in the form of heat. So resistor will absorb that energy from the cell, and it will dissipate the energy in the form of heat unless the cell comes to the safe region of 4.2. So here what happens is the resistor dissipates the energy in the form of heat. So it's a waste of energy. So what happens is passive energy does not require highly sophisticated control. So whenever you have an application where you want to build a cheap BMS, cheap means, what I mean is not a very highly sophisticated, high necessary. You don't need active balancing. Then in that case, people go for passive balancing. So most of the Indian companies, two-wheeler and three-wheeler manufacturers, they have passive balancing only. You can identify when you touch the BMS, it will be very hot, very, very hot when it is operating. Even while charging also it will be hot, because while charging also it will try to balance your cells. So the passive balancing is the one technique mostly used for lower vehicle segment, two-wheeler and three-wheeler. And when you go for a passenger car segment like passenger car or truck or buses, then you have a very bigger battery pack, and the challenges are more. Say, think about Tesla. 4,000 cells are there. 4,000 cells are there in the Tesla Model S and Model 3. So 4,000 cells. I have to control the cells individually. I have to control it. So, but still, what happened is that controllability is there. Actually, when you compare to cylindrical cell and pouch cell and prismatic cell, controlling the individual voltage and individual temperature is very good, very effective in a cylindrical cell. That is why still now Tesla focuses on that compared to the prismatic and pouch type cell. Pouch type cells are very, very costlier. In terms of manufacturing cost, it is very, very costly. If I use pouch type cell, I have to reduce the cost of my vehicle in other components. Understand that? Right? So Tesla saves the cost in the battery cells, and they do innovation and they do improvement in the other parts of the vehicle. That's how the strategy of companies change. So the passive charging is basically discharging of the cell's energy, excess energy, through a resistor. It's a waste of energy, dissipation, but it is useful for lower vehicle segments like two and three-wheeler. I hope people understood got a basic understanding on this particular picture. Right? Let me come back to this slide. Other than the balancing, so balancing is completely done by the cell supervisory circuit. We call it as the slave unit. And report, but the slave unit cannot decide everything on its own. It has to report to the BMU unit, and BMU has the master controller. Basically, the master controller is sitting inside the BMU. So the master controller will tell what is the threshold value, where you have to, whether you can do the balancing or not. Right? All these actuations are been done by the BMU only. And other than that, the very important thing that it is also doing is the actuation of the relay. So day before yesterday, I shown you main relay, pre-charge relay, HVIL. What is HVIL? Do you remember, guys? High voltage interlock circuit. So that high voltage interlock circuit is also controlled by the BMS only. Right? So we have to understand that the complete relays, contactors, how it is controlling, because we have a current sensor. Yesterday, I think day before yesterday, I shown you a battery junction block. Actually, in the junction block, there is one more thing that will come. That is a current sensor. So the current sensor continuously monitor what is the current flow out of the battery pack. From the battery pack, how much current is going to the motor or to the inverter. That current is being sensed by the BMS. And if the BMS understands that the current is beyond certain limit, immediately we call it as over voltage protection, over current protection, over temperature protection. These three are the very important activity that a BMS is doing. Either higher than the certain voltage or lower than certain voltage, higher than certain current or lower than certain current, higher than certain temperature, lower than certain temperature. All these extreme informations are calculated, monitored by the BMS using the sensors, and it decides whether I need to open the main relays or close the main relays. Say someone mistakenly opened the inverter directly without turning off the car. Immediately your HVIL will inform the BMS. So immediately your HVIL will get information, will provide information to the BMS, and immediately within fraction of milliseconds your relays will get opened. So you understood that circle of information. And you remember I told the manual service disconnect, MSD, that is nothing but MSD is nothing but, guys, the difference between manual service disconnect and HVIL. Understand one thing. Manual service disconnect is actually a switch which disconnects even a module to module. Even between one module to module, there will be no connection. That is called MSD. Service disconnect means in between module itself, the connection will be disconnected. But if I am saying HVIL, it means what? Only the vehicle battery pack will be disconnected from the inverter and other components, other high voltage components. But internally, it will not be disconnected. So when I remove the service disconnect, then only internally it will get disconnected. I believe people can understand the difference between these two, right? So if that is why I'm telling, so when you are doing servicing activity, you should not remove the HVIL or all these things. You have to remove the manual service disconnect because internally there will be disconnection between the battery modules. So there is no chances of power output coming from the battery, right? So this is very important that I hope this picture has given a very clear understanding on the battery management system. So these are all the functions that is performed by the battery management system. Maybe in future, if you get chances of more sessions, then we can have more detailed discussions on that. There are so many things behind the balancing part. So many next step levels are there, but for as a beginning level, it is good to understand the functions basically. I hope you got an understanding on the functions of the battery pack, right? All these are words. All the words I have put it in this box, okay? But still, let me just show you the words actually. So we monitor, what are all the things that we monitor in the battery pack? Energy and power management and prediction. So based upon how I measure the voltage and current and I told you, right, the master slave. So everything, whatever I told in the word, it is there in the words here, right? So let me showcase the last final part, the parameters. See, I told it is monitoring the voltage, it is monitoring the temperature, it is monitoring the current. So based on the monitoring of all this information, the battery management system will also do a calculation called state of charge estimation. So what is meant by state of charge? So everyone, I hope everyone have a mobile phone in your hand now, right? So in your mobile phone, you might be seeing, it is showing that my mobile phone, it is showing 13% charge is available in my battery, in my mobile phone. So I am now turning off my mobile phone now. 13% it is showing. This 13% is what it is called as SOC, state of charge. So any participant, can you tell me what is the SOC that is showing in your mobile phone? Just an example, please. Okay, Professor Dilip is telling 78. Chaitanya and Mr. Kasoju, all is 69. Right? So everyone's mobile phone, the SOC is present. So similarly, an electric vehicle also will show you what is the available energy currently. Because this is very important, right? Without the SOC value, I cannot tell my driver how much kilometer this vehicle will be driven, can be driven. Correct? The SOC information is very, very important. And how it is decided? So the SOC is nothing but it is decided based on multiple methodologies. One of the common methodologies is by measuring the open circuit voltage of the battery pack. So what is the voltage of the battery pack? They measure the voltage and based on that they predict the state of charge of the battery pack. Say for example, if I take a 48 volt battery, when I fully charge the 48 volt battery, so let me take a cell. Now this is the question to all the participants. If I am taking a cell, the nominal voltage is 3.75. When I fully charge this cell, what will be the voltage? Generically, I'm asking, what will be the voltage, guys? It will be somewhere close to 4.1, 4.2. Similarly, when I take it as a battery pack, I used to call it as 48 volt battery pack. But when I fully charge the 48 volt battery pack, it will be going to 52 volt, upper threshold. And when I fully discharge the battery pack, it will be going somewhere to 39 volt or 40 volt. That is called lower threshold, right? So that is where, so the depending upon measuring the voltage of your cell, whether it is a 52 volt. So if it is 52 volt means it is called 100% SOC. So like that, depending upon the voltage of the cell, the system determines the SOC of your battery pack. And the next important information that your battery BMS is doing is state of health determination. State of health means what? State of charge means how long, how many kilometers this vehicle will drive. That information is available. That is called state of charge. State of health means what? How long this battery pack will work. Whether this battery pack will work for next 1 year or next 2 year or next 5 year, next 10 year. So with respect to the calendar life of the battery, state of health is one more parameter calculated by the battery pack. So state of health tells the driver that how long this battery pack, the aging of the battery pack can be understood from the SOH index. Right? Without further delay, guys, let me go to a case study, an interesting case study. The last few minutes are there. Let us see a case study. Till now, you have seen so much of information on the battery pack, cell, pack, and the module, and all the BMS and all these things.
Hello and welcome to the Electric Highway. Now in these short videos I'm going to describe how you use the Electric Highway charging network that's in motorway services all over the country. But before you start, there are a couple of things that you need to be able to access this service. The first one is of course the card. Now this is the Electric Highway card. You can apply for this online, you get it for free, they'll send it to your house and you use that card to access the chargers. The other thing you need to do is have a quick look at the map, which is online, and that tells you where the chargers are located, what sort of chargers they are, and whether they're online or not. That's very useful. And thirdly, and probably most importantly, the thing you need is an electric car. This is the Nissan Leaf, a 100% electric car that uses the DC CHAdeMO charger. You choose that option by pressing the button where it says DC. Put your card on the reader and then follow the instructions. The DC CHAdeMO input is the one on the left-hand side in this picture. You gently insert the charge plug into the socket and pull the lever. Push it in and pull the lever. Then you press the green tick button. The charger communicates with the car and very soon it starts charging. The car we were charging had only travelled 30 miles, so it didn't really need a charge. When you want to leave, you press the stop charging button, show your card, and the charger stops. To release the plug, press the top button with your thumb and slide back the catch at the bottom. Then replace the plug in the charger unit. But not like that. If it rains, the plug fills with water, which is not good. The plug needs to go in its cradle, which protects it from the elements. The hook is for the cable hanger to keep everything tidy for the next user. The older model CHAdeMO connectors are being replaced with newer ones that are so much easier to use. Remember to use your card to stop the charge before you remove it. That's done by pressing the yellow button on the connector. Other cars that use the DC CHAdeMO system are the Mitsubishi i-MiEV, the Outlander plug-in hybrid, the Peugeot Ion, the Kia Soul, and the Citroën C0. Electric car charging etiquette. It's really very basic, and it's a whole new lot of manners and behaviour that we've got to learn. Now, number one, which is really pretty basic, is don't park a petrol or diesel car in an electric car charging bay. That's really not good etiquette. Number two, if someone else is charging, don't unplug their car and plug yours in. Wait until their car has finished charging, and then, even if they're not around, it is perfectly acceptable and polite to gently unplug their car and plug yours in. You'll be able to tell if their car is charged by the screen. It will say charging finished. So then you can charge your car. The charger won't be locked into their car. It will unlock when it's finished charging. So there's no damage caused. It's not offensive to do it. People have done it to me and I haven't got upset. Number three is, if you can help someone who's having trouble plugging their car in and you're here, then do help them. Be generous. Show them how it's done. Explain how the system works. Number four is, if you see that the charger has got damage, if it's been vandalised, if something's broken, then give Ecotricity a call. Their number's on the side here. They're open in normal office hours during the week, and explain to them what's happened to the charger. Because even though they can tell what's going on with these chargers, they can't physically see it from their offices. So if you ring them and explain, then they can get an engineer out really quickly and get the thing fixed. And finally, let's try and be mature about this. Let's behave responsibly and set a good example. Now, occasionally there are issues with either the chargers or in particular with the cars, and the fact that they need to talk to each other through quite complicated electronics, and occasionally, not a lot, but occasionally it does go a bit wrong. So just be patient. Try and understand that this is developing technology. It's developing very rapidly. Even a couple of years ago, these weren't as reliable as they are now. They are improving, but it is a bit of a step-by-step struggle. So we all need to help each other to make this system work, because it is remarkable. Every month now, Ecotricity is supplying over 1 million miles of electricity for electric vehicles, and soon it'll be tens of millions. It's extraordinary what's happened in such a short time. So let's stick together, work together, try and make it better.
Today we'll discuss about the charging system. So charging system technology for EVs. So today we know that everyone, so if I talk about electric vehicle, the first question everyone asks, we don't have a quick charging system or charging technology, and then why I would see how I would see electric vehicles. That's how people talk to me, because I meet so much people. So if I meet 100 people, 70% people give negative thought on the electric vehicles, and 30% people give some positive thoughts. What happens is, we understand that, say, charging system technology means everyone expect fast chargers, right? I don't know if I have added that information there, but understand that fast chargers are not there in even developed countries also completely. So before going to the charging system technology, just understand its presence in other countries. So currently, so guys, when you look at the current scenario globally, as we see that all the countries, United States, if you look at, generally, basically, we have the charging systems. We classify into level 1, level 2, and level 3, like slow charger, medium charger, and fast charger. Even United States don't have fast charger. They just have 9% fast chargers till 2020, right? And they are majorly using 56% of the US people. They are majorly using level 2 charger. Who are using electric vehicle? They are using level 2 chargers only, and level 1 charger is somewhere close to 35%. It is the only country, China, where the level 3, that means the fast chargers, are at increasing rate. They are using it in a very increasing rate because they have attained a certain matured stage. Basically, I told you very clearly, people, that we are at a stage where China was 10-15 years back. So remember that it will take time, for India to reach a certain stage of maturity on the charging systems. Even well-developed countries don't have full of fast chargers. So don't think that we have to wait for fast charger and we have to, then only the technology will come. No, electric vehicles will be there, and even if you are not using, there are people using it. So think, if you see the total electric vehicle sales happening in India today, most of the sales are happening in the tier 2, tier 3 cities, not the main cities. It is happening in some of the villages, some of the towns only. It is not in the cities actually. If you check the total sales data, right? So why? Because there is a demand at that place. They don't expect fast charging and all. They expect people at village. They have some small work to go for some small shop. They go for some nearby places. They want to use that. So they don't have too much expectations like we city people have. We people who live in city, there is no limit for our expectations. I hope you people also will agree, if I'm not wrong, because I walk village and in the city. Right now I'm not in cities. I'm far away from cities. I'm living in some village in the town. We all city people, we have lot of everything quick. We need everything instant, right? Totally on the global scenario, you see fast chargers are at minimal rate only right now because the technology is not fully matured. So even in United States, it's right now total chargers 9% only. It is fast charger. So it is expected to go. It is projected that by 2030 it will be 20% of the total charger market. And in China, in 2030, it is projected to be 44% of the total. And India is at a very niche market, will be fast chargers. Early stage right now. So we cannot project anything immediately. But we say that India's market is like next coming years, India will have more market on the level 1 and level 2 chargers only, depending upon the market segment, either it is a 2-wheeler or 3-wheeler. And of course, buses will definitely have fast chargers. And the fleet market, say if I am an operator of Ola Uber, for example, then Ola Uber definitely they'll go for because they have mass vehicle, they have some thousands of vehicles. So obviously they'll create an infrastructure because users are more, right? It's not like one car, one user. They have so much of cars that will be running in Ola Uber kind of market. So there you can put up, you can invest on the infrastructure, and after every day hundreds and thousands of cars can be charged basically. And I have seen some of the companies in Bangalore. Since I was there in Bangalore, in some of the companies in Bangalore, they already have their electric vehicle fleet for their employees. Maybe you people would have seen some of the cars. So there are some companies which have 50% fleet electric vehicle cars and 50% petrol diesel cars. So like that, they are bringing down their carbon footprint end of the day. So let's consider, when someone is working on a charging system project, we have to have some design considerations basically, right? So when you have the overall level, top level of requirement, what is the consideration? So when you look at the charging system, basically we have the total power electronics part. So the power electronics part, so how and better the power electronics part is being done. And the standardization means, what I mean is standardization means like with respect to because the charging system technology has special standards and regulations, and these standards and regulations will change from country to country. The standards are quite different in India and the standards are quite different in China. So the standardization of the charger is also very important, and that is not 100% happened in all the places. Right now, till now, there was a war going on. Which charger plug I have to use for the whole world? So China was telling we have to use our charger plug. Japan was telling you have to use our design. So like that, it was a big war was going, and recently the war came to an end. So we'll discuss about that in the end. So the charging infrastructure. So how much space that your charging system will need. and the total power output depending upon your, basically the fast charger, slow charger, medium charger, all these things are classified depending upon the total charging power output. So what is your power level, and whether our grid is having the ability to withstand such kind of power level. So all these considerations have to be taken when we are designing a charging system for a particular electric vehicle application. So yesterday we talked about lithium batteries. So basically the charging system methodology is quite similar to the lead acid batteries also. So both the lead acid battery and the lithium ion battery follow the methodology. We call it as constant current and constant voltage methodology, right? So I don't want to go deeper into the reactions, but understand that we have a charging discharging process, and whenever the charging discharging process happens, there is a movement of ions inside through the electrolyte, and at the same time there is a movement of the electron through the load. So what happens is, this is the methodology that you follow in lead acid battery and we follow in the lithium ion battery. What happens is how the charger works basically. So the charger follows a constant current, constant voltage methodology. So do you guys remember what was the threshold voltage for a cell? Yesterday I told the nominal voltage is 3.75 for a cell, and the upper threshold voltage can be somewhere close to what value? Yes, 4.2 volt. And what is the lower threshold value? We have taken some example. I've told some examples. 3.0 volt. So in that case, what happens is your cells actually, say for example, my cell is almost in the range of 527 volt, 2.7 volt. And when I'm charging the cell, what happens is, initially I'm supplying a constant current. The current value lies somewhere in a particular range, and then after a particular period of time, the current starts coming down slowly, little by little, and my voltage becomes constant at that time. So initially what happens is my current is staying constant, and my voltage is keep on increasing. Actually it is changing, and after a period of time my current varies and my voltage becomes constant, because it reaches the threshold voltage of 4.1, 4.2. So in that range it becomes constant, and at that time my battery's AH will keep on steadily, it will decrease, but at the same time there will be a current flowing to the battery. So we call the charging rate as 1C, 2C, depending upon how much current we are providing, right? So basically if you take your mobile charger, so mobile chargers, I believe those are all 2 ampere chargers, right? 2 amps chargers you would have seen. So when you any equipment, if you take any battery in your mobile phone also, if you open and see, they have mentioned what is the in my mobile phone it is mentioned input is what is the input that I can give for the mobile phone is plus 5 volt and 2 ampere. So totally 10 watt is what I can supply to my mobile phone. So the charging methodology that is used generally in the lithium batteries is the constant current and constant voltage methodology. So what happens is, when during the constant current time, for example, if you take lead acid battery, in the initial stage, during the constant current stage, the lead acid battery charges up to 70%, and the remaining 30% is filled with the slow top-up charging. We call it as the lower current charging. This is called the top-up, very slow charging, and in this period 70% of your charging happens in this period. The last 30% only takes most of the time, right? And when you talk about the lithium ion battery, in that case what happens is, the higher voltage per cell, tighter voltage tolerances, right? So basically depend upon what is the total depend upon total voltage, the total voltage of the nominal voltage of your cell and the total peak voltage. So there are some cells will be having 4.2 volt as their peak volt, some cells will be having 4.1. So it will change from one cell to another cell. That means types of cells, NMC or LFP, and different cells we have seen yesterday. So not all the cells will need 4.2 or will stop at 4.2, right? It will change from one cell technology to another technology. And when you are charging the cell, there will be an increase in the temperature of the battery as well, right? And according to that increase in the temperature, basically there will be some losses, and the losses will be in the form of heat. So how the heat is generated? You can see that if it is a lead acid battery, the charging temperature range is somewhere minus 20 degrees Celsius to 50 degrees Celsius, safe temperature. And whereas the lithium-ion batteries, you can see 0 degrees Celsius to 45 degrees Celsius. It is a safe temperature for them to get charged. And above which or below which you have to, it will be very difficult, and you can see there will be losses in the charger basically. So below freezing, what will happen? No charging will be allowed basically. So that's why in cold countries, especially countries like Canada and some of the European countries, they still don't have pure electric vehicles effectively running. They all face losses in their particular area. So the temperature is very, very important in charging system where we are charging it. What is the temperature range at the place where the vehicle is standing? That becomes a very important role. And in that perspective, the temperatures what we are seeing in India is not a major impact. Unless until if you are providing some ventilation, there is no major impact. We will understand in coming slides. We will understand how the control system decides when a vehicle can be charged and what are all the problems that it will face. All the questions we will answer now. So when you talk about charging system, guys, there are two classifications we have. One is on-board charging and one is off-board charging. So basically, off-board charging is designed to transfer very higher kilowatts, much higher kilowatts of power, basically more than 50 kilowatt. It is more than 50 kilowatt. So when you have charger which is transferring more than 50 kilowatt and ampere rating will be more at that charges, those are called off-board chargers. And we also have on-board charging basically that comes under the 15 kilowatt or 10 kilowatt capacity. Sometimes up to 22 kilowatt people go up to 22 kilowatt. We call it as on-board chargers. So what happens is here 3.3 kilowatt one model is there and 6.6 kilowatts models are there. So what happens is basically 3.3 kilowatt means, what is that means? It is a 10 our home sockets basically. What is the ampere we have in our home sockets, guys? What is the ampere current? Yes, 15, 16. So those are all coming under the level 1 charging sockets. Those are all coming under the level 1 charging sockets, and it will be like a much very slow, and it will take minimum, say for a two-wheeler, it will take minimum 3 to 4 hours to completely charge a vehicle. We will discuss more deeper into the coming slides. But understand that the onboard and offboard charging, that it is onboard is basically a lower kilowatt charger and offboard means it's a higher kilowatt charger. So when you classify that, they are like, we call it as AC and DC charging. So by the word itself, by the name itself, we can understand that AC charging. So AC charging in the sense we are giving AC input to the vehicle. What is the input you are giving to the vehicle? That is what coming under the name of the charging. So AC charging means I am giving AC input. DC charging means I am giving DC input. So in AC charging, what happens? I am giving the AC input from my grid into the vehicle, and inside my vehicle there is an onboard charger. So that is nothing but an AC to DC converter. So that AC to DC converter converts my AC power that I am getting from the grid into a DC output, and that DC is given to the battery. Whereas DC charger, it directly this conversion, whereas in the DC happens inside the charger which is present outside the vehicle. It has DC fast charger. So in this charger, conversion happens inside this box, and you get the DC output in the cable. And these cables obviously they will be in orange color because you know why. So those high voltage cables are being traveling from the charger, and they directly give the power to the battery. They don't have any onboard charger in between. So that is what we call it as DC charger or DC fast charger, right? And even in DC charger in India, especially India is a very special country, I told. So in India we have developed a slow charger in DC also. So we call it as DC slow charger. So in India we have AC slow charger, DC slow charger, and AC medium charger, DC medium charger, and DC fast charger, right? Let's understand, because the battery needs DC. End of the day, the battery needs DC. So if you give DC directly to the battery, you will be able to quickly feed it. If you are not feeding it directly, if you are feeding it through a AC-DC converter, then obviously you cannot do it faster, right? There is a limitation on the power electronics. So when you have an onboard charger, when you have an AC charger, it cannot be very quick because there is an onboard conversion that should happen. But if I have a direct DC supply to the battery, then there is no conversion inside the vehicle. So So the time, it will not take too much time to charge the battery. So when you look at a AC charging system, the charging current, we can classify that into two categories, level 1 and level 2. So the level 1 charging will be like 12 ampere to 16 ampere range, the current rating, and the voltage rating will be 230 volt in India. It will be like 230 volt AC and 12 ampere to 16 ampere range. And the level 2 chargers are basically, the level 1 chargers are basically used in residential areas. I told you very clearly, it is in a home, in our home based system. So level 2 chargers, what happens is, the level 2 chargers, it is specifically suitable for commercial spaces like shopping mall, theaters, shopping malls, and offices. So our working officers, all these places are apartments. So these kind of places are suitable for the level 2 charger, which can be quite quicker, and it can handle up to 80 ampere current, 15 ampere to 18 ampere current. Higher current is possible for level 2 chargers. And you can see, this is the vehicle. This is the outside environment. So outside we have the EVSE. So don't confuse EVSE, nothing but it is the charger, electric vehicle supply equipment. So we should not call it as a charger. Basically, it should be called as, technically it should be called as electric vehicle supply equipment, EVSE, as per the terminology given by IEEE, right? So there are certain terminologies that we should follow as it is. We should not change the name on our own. So try to use this word instead of using charger. Always try to use this word called EVSE, electric vehicle supply equipment. So the grid, from the grid, your AC supply comes to a EVSE, and your EVSE supplies the AC directly to your vehicle, and your vehicle has an onboard charger which converts the AC into DC and then supplies that to the BMS of your battery. And remember that without the knowledge of BMS, battery cannot be charged, should not be charged, right? Because yesterday you saw that there was a current sensor placed. There's a current sensor that was used by the BMS to monitor the things. So obviously the line going between the converter to the battery, the onboard charger to the battery, should be going through the BMS only. The BMS should be able to monitor that. That is very, very important. That is a level, basically the level AC charges are of level 1 and level 2. So basically all the vehicles will have an onboard converter, especially passenger cars. I am not talking about 2-wheelers and 3-wheelers. When you talk about passenger cars and trucks and buses, they will definitely have an onboard converter, and even that onboard converter will be connected to the cooling system of your battery also. So whenever the charging system turns on, even these components also should be cooled, because they generate a lot of heat when they are working because of the AC-DC conversion. So what happens is, in the DC charging system, the current values are somewhere close to 400 amperes, and the voltage will be like in the range of 300 voltage to 750 voltage. So you people can calculate 300 into 400. So it is somewhere in the range of 120 kilowatt is possible for the charger to work. So today we have up to 250 kilowatt fast chargers are available in the market, starting from 50 kilowatt for cars up to 250 kilowatt for buses. People are using fast chargers. It is there in the market from companies. There are some companies, I'll name it in the last few slides. So understand that DC charger, the AC-DC conversion happens inside the charger itself, and the output is directly DC, so that it bypasses the converter. Let's dive deep into each and every charger now. Let's understand each and every charger in a more deeper way. So when we talk about, this is what a slow AC charger, in order to tell you, I want to show that before itself. So this is the AC charger that I want to tell you. So this is basically the AC chargers manufactured by Delta Electronics. There's a company called Delta Electronics. It's a Taiwan-based company, but they have their manufacturing plant in India, in Hosur. They have a manufacturing plant in Tamil Nadu and Karnataka border. So they have a manufacturing plant. They started manufacturing slow chargers and fast chargers also. They're seeing the demand in India right now. So let us jump into this, guys. Okay, when you look at AC charging, let's dive deep into the AC charging. What is there inside a charger? What is there inside this system? Let's understand that now. This is the grid. We know from where the electricity is coming, and we know where it is going to the vehicle. So between the vehicle and the grid, we have the charger. What is there inside the charger? So basically the charger has a current and voltage monitoring system. So the system controller takes care of the whole activity of the charger, And basically what it controls the amount of input power coming into the charger, and it controls the amount of output power going out of the charger to the vehicle, and it makes sure that it is also supporting the some of the safety relays, because your charger will have many safety relays inside, switches. So in terms of any danger, if there is a small accident happened or any danger happened during charging process, immediately the charger will detect that and it will turn on, that means it will open the circuit by using the relays. So we will have a relays inside the charger, and we will have a separate communication protocol. The vehicle communication system will be there. Depending upon the total type of charger, we will have a communication system ranging from different methodology. So sometimes we are using like a CAN communication system, CAN protocol, right? So we use PWM signals to transfer the information sometimes. So depending upon the category of charger, they go for different communication protocol systems. And there is a human machine interface, So if I have a charger, I should have a display, right? So the display should tell me what is the total power output going, what is the total time that the charger will take to charge the vehicle. So all the information should be given to the customer, the human. So there is a human machine interface, HMI interface is there. That is also part of the charging system. And we also have an AC DC converter. And I told it is an AC charging. What is this then? What is this AC DC converter? I hope you can understand this by seeing the arrow. What is this AC DC converter doing? So we have the controller. So basically the controller components need the 5 volt, 12 volt inputs basically to run the controller components, and that is what we call the AC DC converter. So when we have all these components that comes under the AC charging system. And similarly, these are the wordings that I have shown you, whatever I explained you in the previous slide. And the DC charging system. What happens here? What is the difference of the DC charging system? The difference is we have a special, we have a power factor correction stage, and we also have a DC-DC converter. So here inside the DC charger, we have a DC-DC conversion happening inside, and the remaining things, system controller, vehicle communication, HMI, the human machine interface, everything remains same. And the output will be DC in this charger, whereas in the AC charger, the output is AC. And I'll talk about the pilot and all these things in the coming slides. There are so many things that we have to discuss in this. So basically, these are all level 3 chargers, and in the range of 60 kilowatt, 50-60 kilowatt. So as I told, we have a power factor correction. Let me go to the next important picture. It will be a broad view of the same picture. Look at this picture, guys. This is a quite broader view of the 3.3 kilowatt DC charging system. Basically, it is because I told in India we have slow charger also in DC charger. Okay, in India we have slow chargers in DC category also. Whereas if you go to United States, Europe and all, they only have AC chargers in the slow category and DC chargers in the fast category. Right? Let's look at this example. This is basically a 3.3 kilowatt charger, and you can see that initially what happens, we are taking from the grid. We are taking a single phase line, and it initially goes to the EMI filter. The first stage of the charger is the EMI filter. So electromagnetic interference filter will be there. And after that filter, we have the rectifier stage. We have the rectification stage, the diode bridge rectifier. So, but what happens in this, so initially what is the input? It's the AC input. And what happens in this rectifier is nothing but this AC input is converted into a pulsated DC output. It is brought down into a pulsated DC output, and that pulsated DC output is converted into a stable DC output, what we need to give supply to a battery of an electric car. So overall, you have to understand that initially you have an EMI stage, EMI filter stage. So the EMI filter stage makes sure that the input AC source is properly EMI filtered, so that it will not have any impact on the charging system. And the next stage is the bridge rectifier. Here I told that it converts your AC into a pulsating DC. It will not purely convert into a pure DC, but initially it will convert into a pulsating DC. And here you can, one more stage, we have the auxiliary flyback DC-DC converter. And this is what is going for the controller. So you know what it is. So it is basically converts, it brings down your 12 volt, 5 volt, Sometimes 16 volt is required for some of the components. So depending upon the voltage requirement of the power electronic component sitting inside your controller, you have to have a auxiliary flyback DC-DC converter. So that is taken from this output, and because the PFC is being controlled by a separate PFC controller. So what is meant by PFC? Maybe for the most people may be aware, but for the beginners, I'm asking the question: what is meant by PFC? So power factor correction. It keeps the input and the output in phase with each other. And what happens is basically, if you do not have a power factor correction, if you do not, we do not have a proper power factor correction, then there will be a huge amount of loss basically on the input, total amount of input power what we are getting. We will not be able to get the output power properly. So if we do not have a proper power factor, especially the industrial applications where heavy machineries are going on running, those industry machineries and all, like they can have some impact on the total grid from where they're getting the supply. So that is why it is a mandatory, as per the regulation also, it is said that power factor correction should be there. A charging system layout, I'll explain you by part. So basically we have the first part is your EMI filter. So basically the EMI filter, it reduces your differential mode, right? It reduces your differential mode and the common mode noise in your system. And in order to meet the the EMI EMC regulations, there are some electromagnetic interference and compliance regulations are there, and that in order to meet that, you have to reduce the differential mode and the common mode noises which are arising from the system. And at the same time, it suppresses the EMI, because if they are not suppressing the EMI noise, what happens is this might lead to the malfunction of the whole system inside the charger, right? And basically it helps all the power electronic components to be safe, to work safer in the system. So the first step, as I mentioned earlier, is the EMI filter, right? And second stage is what we call it as the AC voltage input sense function. So initially we have to measure, what is the total input voltage that is coming to this watch on it, and that information has to be provided to the controller. So basically it reads the total input root mean square voltage. So we have the master control unit, MCU. You can see at this end, this is the master control unit which takes care of the whole function of your charger. So this master control unit will limit the input current in case the input voltage is lower than the certain threshold voltage. And it also performs the over voltage protection. So basically in your system, if it comes to know through the voltage sense, if it comes to know that the voltage is beyond certain threshold, then this MCU unit, controller unit, makes sure that it protects the system. So what happens in the next step? So basically we have the auxiliary power supply, and I told that why we need a auxiliary power supply. We have the flyback DC-DC converter. So basically it takes it gives an output somewhere like 16 volt and 12 volt outputs from the input voltage. So what happens? That means after the rectification, the initial rectification stage. So what happens is here, the 12 volt and 16 volt inputs are used to drive the gate drivers for your MOSFETs or your IGBTs, whatever the switching devices might be. So you need to run this switching power devices using a gate driver. So to run the gate driver, you have to provide with some power, and basically that is coming from your auxiliary flyback. That's what we called as controller components. And you need some 12 volt input for the controller part, the other controller part which is controlling the DC-DC converter side. So basically we have totally 3 conversions happening in the flyback DC. One is the 12 volt output. 12 volt output that is going to the MOSFETs. These are the MOSFETs which are used to operate the system here. So these MOSFETs are run by the gate drivers, and they need a 12 volt input, and 16 volt inputs are needed to the isolated gate drivers, and 6.5 volt is required for the low dropout regulators. We also use some LDO for the tracking regulators. So we call it as the LDOs. Those LDOs are also coming into picture in the charging system. So they need somewhere close to 6.5 voltage to operate. So what happens here? So initially we were talking about the PFC. So here is where you can see the PFC system. And what happens, what is the difference between a conventional PFC and this here is we use a system called interleaved PFC. In the automotive electric vehicle charger, we use something called interleaved PFC. So what is the interleaved PFC? So we split the system. Basically, you can look at this clear picture that you have an inductor, you have the switching device, you have the capacitor, and you have the diode. So this resembles nothing but a PFC system. And here what we are doing is we are splitting the PFC into two stages, two separate stages. So what happens is, end of the day, you get the output. So it is basically interleaved. Interleaved means it is splitting, it is sharing, you can say. And because of that, why people are going for interleaved PFCs, basically overall they are able to achieve a stable power output and a power density in order to meet the power density demand. Even day before yesterday, I told you that there is a power density target for the motors. There are some power density targets for the system. So similarly, in order to reduce the total amount of ripples that is coming out of the system, people are now going for the interleaved PFC systems. And you can see that this is a interleaved PFC stage that is in the part of the charging system. And after that, what happens? You get a output from the interleaved PFC, and you have a separate, and immediately you have a current transformers. You have some current transformers, and you have some isolated amplifiers. And these amplifiers, isolated amplifiers, are basically voltage measurement systems. Voltage measurement systems. So these are placed between the, placed at the input of the DC. So before the final DC-DC conversion happening, before that, in the input side, we have an isolated amplifier which measures the voltage. And you have a current transformer which measures the current. So these inputs are provided to your master control unit, based on which the total control of the charger system happens. So you have a isolated amplifier which does the voltage sensing. It measures the voltage in the input side of the DC-DC converter, and the current transformer which measures the current in the input side of the DC-DC converter. And after this, what happens? After this, what happens? We have the DC-DC converter. And this DC-DC converter basically converts the pulsating DC, which is not stable enough to meet the battery pack demand. Say, look at this, here is the battery pack that we are charging, your electric vehicle battery pack. So before if it has to, we also have the isolated amplifiers here, as well as we also have isolated amplifiers here to measure the the output voltage that is coming from the system. So what happens is we also have an op amp. So what happens here? The isolated amplifier reads the current input and converts it into a differential output, and your operational amplifier just converts the differential output into a single output, which can be understood by the MCU unit, the master control unit. So what happens is, on the output side, see, basically this is your DC-DC converter. In the DC-DC converter output side, we have a voltage sensing, and that measures the voltage. And at the same time, on the input side of the DC-DC converter also, we have a voltage sensing. So these two informations are provided to your master control unit. You can see that the voltage references coming from the current references. Based on all this information only, the master control unit decides or determines that the current state of the charger, how it is working. And also, other than all these things, as I earlier told, that the master control unit also controls the relays. You can see the relay which is sitting here. So in terms of any danger, happening, let's say, for example, you have kept your charger charging on the road. It is standing on the road or somewhere in a parking garage. Some other car or some vehicle came and crashed your vehicle. Right? So what will happen? Immediately the charger detects the system, and it will immediately, the relays will be opened by the system, and we have a separate unit for that. And it controls all the over voltage protection, over current protection. Everything is being maintained by this relay, which is controlled by the MCU. And we also have temperature measurement units, especially at the switching devices. So the MOSFETs are being placed with a temperature control system, and these temperature sensors give the temperature signals to the master control unit, and the MCU unit determines whether the MOSFETs are running at their very higher end threshold limits. If they find that the threshold limits are being reached, then immediately it will turn off the charges, basically. So let's understand the operation in the later slides. What is the communication happens inside? But understand, these are the components that makes a charger. So inside a charger, you have a EMI system, So you have a relay unit, which is to safeguard the system in terms of any over voltage or any problems. And we have a stage called PFC, and in this PFC, we have it as interleaved PFC stages, as I mentioned, to reduce the ripples that can come out of the system. And after that, we also have a sensing systems like voltage sensing and current sensing at the output of the PFC. And that means that is the output of the PFC, means it is the input of your DC-DC converter. So this is the DC-DC primary side, and this is your DC-DC secondary side. So basically, these MOSFETs are operated by your gate drivers, right? And these gate drivers are controlled by your control unit. And all these informations are now taken care by the communication network, and that is being communicated to and from the master control unit. That makes sure that the information travels from all the unit part of the charger and even to the vehicle as well, right? Because we need to provide some information to the vehicle also. So this is the part of the charging system, what is there inside a charging system. So when we look at this chargers, as I mentioned, in India we have fast DC chargers also in this. So we call it as Bharat AC001 slow category and Bharat DC001. So Bharat AC001 is basically a 10 kilowatt charger, and Bharat the DC001 is basically a 15 kilowatt charger. And the output is basically the AC001, the output is 230 volt given to the vehicle, and on board that means it converts, it don't convert it does not convert AC to DC in this charger. It just gives the AC output, regulated AC output. And basically these chargers have three guns. That means 3 outputs can be there. Every output will be having 3.3 kilowatts. So 3.3, 3.3, 3.3, almost it is a 10 kilowatt. We call it as 10 kilowatt chargers. That is how it is called as 10 kilowatt chargers. And the fast chargers and medium chargers, they like 22 kilowatt are all medium chargers, and fast chargers are basically 50 kilowatt, minimum 50 kilowatt it should be. I'll talk about the CCS and what is this and all in the coming slides. But understand that this is the voltage rating in which it will be working. So this document is taken from the government regulation. You can go to the website called National Electricity Authority, Central Electricity Authority, CEA website. You can see the guideline provided by the Central Electricity Authority in terms of the charging system technology. So when we look at the level 1, level 2, level 3 charger, when we compare it with a vehicle, say if it is a Nissan Leaf, for example, if I do charging of a Nissan Leaf which is having 32 kilowatt hour battery, with the level 1 charger it will take 16 hours. If I use the same vehicle for a level 2 charger, it will take 5 hours of charging with a 30 amps current. And when I provide a DC fast charger, then the total time it takes to charge the Nissan Leaf is 20 minutes, just 20 minutes to charge up to a 32 kilowatt of power output. And up to 80%, I told you initially that fast charging cannot be sustained for full complete 100% charge. So only up to 80-85% it can be charged. And after that, it has to be a slow charge only. See, we understand these are the different pins, different plugs configurations available in the market. So this is the pin, this is the plug coupler. We call it as coupler. We should call it as coupler as per the regulations provided by agencies. So the coupler looks like this for a DC Tesla vehicles, and the coupler that is used by Japanese standard, it is called as CHAdeMO. That is called as it's a Japanese standard, charge on the move. And this standard is now followed in even European, US and all the markets also. And very recently, some of the vehicle models, they have accepted that they will start using the European chargers. So these are the European chargers basically. They call it as combined AC DC chargers. So these chargers can do both AC charging and DC charging. Upper side you will have AC charging, and the down you have AC DC charging. And this one is the GB/T, which is a Chinese design, Chinese standard, that is called GB/T standard. This is especially designed by Chinese, and there are many OEMs across the world who use this charger also, especially fast charging. Right? Let's understand what all those couplers are doing. Let's understand that. See guys, when you open this charger, look at the coupler. This is an example of a AC charger. These couplers have 5 pins, for example, and these 2 are the power pins. These 2 are the AC power pins, and one of the pin is called the communication pin. This third one is the communication pin. We call it as communication pilot pin. We call it as communication pilot pin. This is the pin through which your charger communicates with your vehicle and the vehicle communicates with your charger. This is the pin configuration through which it happens. And the fourth pin is the proximity pilot pin. It is called proximity pilot pin. Means it detects the charger with the vehicle. Means it detects a vehicle basically. When I connect this charging coupler with the vehicle, this is the pin which detects that there is a vehicle is connected to this charger. It is called proximity pilot pin. And the fifth one is the ground pin. So you have the AC power pins and you have the ground pins and you have the communication pin, communication pilot pin and the connection pilot pin, connection pilot or the proximity pilot, what I mentioned. And this will change from one standard to another standard. And if you look at the level 3 fast chargers, basically in the level 3 chargers look like this. In this case, 2 main power pins and 2 communication pins are there. And here the proximity is carried out in different way. So here we can have a latch. You can see that there is a latch and there's a release button. So whenever the user, and you can see when from where it has been described, where it has been inspired. Can you people tell? Where does this charging plug coupler is being inspired from? So do you remember the petrol stations? Yes, the petrol station. So there we have seen. So these couplers are basically designed as per a standard called SAE J1772. SAE J1772. That is the standard which talks about the coupler design, how the coupler should have, how the pin configuration should be given, how the communication pin should work, what the proximity pilot should work. So that is all the standard recommendations are provided in the SAE J1772. That is the international standard that people are following. And when you look at the combo charger which I told you, these chargers can handle both the AC plugs and DC plugs. So you have the, as I told earlier, the AC plug is there at the top and bottom you have the DC plug. Basically the charger coupler will look like this. These charger plugs are mostly used in the European market. In the European market it is widely used currently. Combined, we call it as combo charger. So combo AC and DC charger. And Tesla has its own charger design, but at the same time it meets all the regulatory requirements provided by all the regulatory authorities, either SAE or IEEE and your electro-technical commission standards. So all these standards are being met by the Tesla fast chargers. Their configurations are quite different. So communication pins are there, the proximity pin is here, and the power pins are here. Different approach on this, the vehicle. Hello. So when we talk about the communication that takes place between the charger and the vehicle, how the charger communicates to the vehicle. So in the charging system design, I've shown you the charging block that there is a communication system. So what happens is, as you see, this is the charger side. This is your vehicle side. Both are having the male and female connections. The 5 pins are there, for example. So you have the power pins and you have the ground pin. You have the pilot pin. That means your communication pilot pin and the proximity pilot pin. So what happens is when the person connects the charger, to your vehicle, immediately first thing what happens is this proximity pin closes. The proximity pin gets connected. The moment the proximity pin gets connected, what happens? The moment the proximity pin gets connected, the control unit inside the charger, you remember they had the MCU. So that the master control unit inside the charger communicates with the vehicle and it understands what is the state of the vehicle currently. How it communicates? It supplies some input voltage. It supplies some plus 12 volt input voltage into the charger, and based upon the feedback signal that it is received by the charger, by the controller, it determines the state of the operation of the vehicle. What happens, say when I am giving 12 volt plus 12 volt input, it is in standby condition. And when I am giving a 12 volt input, I am getting a feedback of 9 volt plus 9 volt output from the vehicle. That means a vehicle is detected. A vehicle is detected. That is called status B. And when I am giving a 12 volt input, I am getting a feedback of 6 volt. Then it means that it is called as vehicle is ready for charging. Who is telling that the vehicle is ready for charging? It is the BMS. So here the vehicle, what happens is the charger and the BMS of the battery pack communicates. So whether the BMS is able to, what they communicate in this stage actually. What they communicate is the charger tells the vehicle that I can supply 15 kilowatt of output or 50 kilowatt, 50 kilowatt of output. And the vehicle BMS gets this information. The vehicle BMS has a CAN system, right? So basically it communicates back that I can only handle 30 kilowatt. For example, I am a vehicle which can handle only 30 kilowatt of power, but my charger is telling I can give you up to 50 kilowatt, right? So based on the information provided by the vehicle, based upon the information received from the vehicle, the charger determines, okay, I give 30 kilowatt. How that is determined, I'll show that in the coming slides. So depending upon the feedback signal coming from the vehicle, the charger understands what is the status of the charging, whether the vehicle is ready for charging, whether the vehicle is detected, and if the feedback signal is 3 volt, I'm giving a 12 volt signal to the charger through the pilot pin, and I'm getting a feedback signal as 3 volt. What it means? It means that the vehicle tells the charger that it can charge, but it needs a ventilation. It is connected, but it needs a ventilation because currently the vehicle is placed in a temperature in an environment where the temperature is very high, so that it cannot accept the charging. So it informs the charger that it needs ventilation, and immediately your charger will give an error code in your monitor that the vehicle needs ventilation, or the total area where they have placed the vehicle, it is completely closed. It means it determines the temperature of the environment. Basically, it needs a ventilation. And if the output voltage, if the feedback signal is 0 volt, it means that it is not connected, it is shut off, the charger is shut off. And if the signal is like minus 12 volt, it is an error signal. It is an error signal. That means there is a system error in the whole system. This is the status diagram, status chart that is provided by SAE J1772. So all the charger manufacturers across the world follow this J1772 standard protocol in order to design the charging system. Right? I hope you people are getting the point. So how I'm giving 12 volt and I'm getting 9 volt and then 6 volt, how it is happening? Because the vehicle side controller communicates with the vehicle using the resistances, different resistors. When the vehicle is giving a 12 volt plus, when the charger is connected to the vehicle, initially it connects a resistor called 2.74 ohm, so kilo ohm, 2740 ohm resistor. Because of that, it gets converted to 9 volt, and similarly, whatever the resistor I am connecting with the vehicle to the connector, to the input, the different communication signal goes there. So whatever the vehicle want to communicate, accordingly the resistors will be actuated by the system using the switches. And basically I told the proximity switch, right? The proximity switch. This proximity switch determines whether a vehicle is connected or not. How that is determined? Using this resistor. So when the vehicle is connected, a resistance input will be coming, and based on that input, your proximity system will close this switch. So then only your charger will start working. So people have a question, sir, when I connect to the charger, while connecting, will I get a arc? Will I get a spark from the charger? Whether that will happen. So basically these are all high voltage systems. So what they do is, only after proper connection is being established, then the switch will close, the S3 switch. This S3 switch will close, and immediately then only your power flow will start from your battery to the vehicle. Till that, no power flow will happen. So that is for the safety purpose we have it. Right? These are the words. So what happens is, how the vehicle and the charger communicates. So basically the vehicle gives a signal, and based upon the PWM signal output that I am getting from the vehicle, the charger determines what is the current output. Say for example, if my charger is giving a PWM signal like of this width, for example, I am giving a PWM signal of this much width, and I am getting a feedback from the vehicle which is 16% of the input signal which I gave. So then the charger will understand that. The vehicle only can withstand maximum 10 ampere current. If the vehicle provides a feedback signal of 25% of the input PWM, because input the PWM signal is provided by the charger, and out of the total width, 25%, if it comes back as the feedback, it means that the vehicle is telling that it is 16 amps that the vehicle can take. And similarly, if the feedback comes like 32 amps, it means what? 50% of the PWM. So if I'm giving 100% PWM, 50% of which comes back to me, it means what? The vehicle is saying that I can handle 32 ampere current. And if it is more than 90% of the PWM signal comes back, it means that the vehicle says to the charger that I can handle fast charging. So this is the way through the control pilot pin, this is the way the vehicle and the charger communicate with them each other. So these are all the wordings, guys. So don't think I'm skipping. These are all the wordings which I explained. So just have a look at it. So the proximity pin and these are the things I have explained in the wordings. And I will talk about the communication standards in the coming slides. So basically, you will have so many communications. That means you have some standards and regulations. Before that, we'll talk about some manufacturer. For your understanding, there are some manufacturers in India. Basically, they are not from India. There are few companies which are from India. Like there is a company called Charge EQ Point, which is based out in Bangalore. In Bangalore, there are so many manufacturers now coming in the charging system domain. But right now, well reputed companies in that sense, Delta Electronics, they are there in this market for so many years in the charging market. So these are their brand. These are their charging range, 7 kilowatt to 22 kilowatt, slow and moderate charger. And these are their fast chargers. The fast chargers will be like 25 kilowatt to 150 kilowatt. So the Delta DC-DC charger has a range of like up to 150 kilowatt. Currently they have models. Models are available in Delta company. And other than Delta, even Delta also does something called site management system. Site management system means what? For example, if in Bangalore, I have say 100, 200 chargers at different places. So one at Rajaji Nagar, one at Shivaji Nagar, one at Magadi Road. So different places if I'm placing it. So I want to understand sitting at one place, right? Sitting at one place, I want to understand the whole charging system network, how it is operating, whether any of the charger has got into any problem, whether all the chargers are working, and how many of the chargers are being currently used by the users, how many of them are idle. So all this information I can understand. This is called site management system. And so Delta Electronics also provide this as well. They also provide this also with their charger. So if a company buys 100, 200 chargers, then they also provide a site management system also for them. Similarly, ABB is one more competitor for the charging system technology. So ABB is a special company, especially for fast charging system, fast charging technology. And you wonder that it won't be a surprise that most of the ABB people, the top people who are developing the chargers are all Indians. Even in Delta Electronics, especially ABB. Most of the people who are sitting inside ABB are all Indians who are working there and developing the charging systems. When I had some interaction with some of the people who develop the main algorithms behind the charging system and all the things. So based on interactions only we gain all this small amount of knowledge what we get. So basically the ABB standard, ABB has a model called Terra 54, and this is the currently the most selling charger in India right now from ABB. So most of the government tenders, all these things, Terra 54 is the charger. Basically this charger has 3 plugs. One is a CHAdeMO plug, one is a combo plug, and one is your AC plug. Like you also have a GB/T plug also. Depending upon the user, whatever they want, they can provide it. So there are different charging plugs possible. It's not like all 3 plugs will not be same. One will be different plugs will be there. Depending upon the customer requirement, they can provide you with different plugs. And basically, these fast chargers can charge your vehicles in 30 minutes, 20 minutes, in minutes of time to hours of time. Look at this. This is one more car. We know Siemens. Siemens is also having a product and the charging system, that is the Siemens home chargers. They are in the range of the input voltage for these chargers will be like 230 volt, and the output currents will be in the range of 32 ampere. Up to 32 ampere it is possible for these chargers. These are all moderate chargers, basically, not a very slow charger. These are all moderate chargers. And look at the IP rating. That is very, very important. These chargers have minimum IP56 rating. That means they are not dust tight completely. Understand? They are not completely dust tight. They are IP56. They are not IP67. So they are not completely dust tight. And we'll talk about the standards. The cord, the connector, I told the SAE regulation. Similarly, you also have a regulation called IEC 62196, followed by some company, the IEC regulation. International Electrotechnical Commission standards are there, 62196, which talks about the charging cable. And we also have an Indian company called Exicom, which manufactures charging system. This is an Indian company based out in North. They are based out in Gurgaon, and they also have their offices in Mumbai. So currently, this is the Indian company which is they are also selling lot of numbers of chargers for most of the government tenders right now. So they are competing with ABB and they are competing with Delta Electronics.